Good morning and good evening. Welcome to the Moonshot International Symposium for Goal 6. Thank you for joining us today. Today's main agenda is as follows. First, we will have keynote speeches from our two distinguished guests. Then we will hear an overview of Moonshot Goal 6, followed by presentations on the 7 individual research projects. For a more detailed agenda, please refer to the Moonshot website. Before we begin, I have a brief message regarding housekeeping requests. We welcome your questions. Please use Zoom's Q&A function at the bottom of your screen if you wish to submit a question or comment. We welcome your input either in English or Japanese. Due to time constraints, we cannot answer all the questions submitted live during the symposium, but all input will be shared with the speakers. And finally, we kindly ask that you do not record or redistribute any of the content presented here today. So, without further ado, I would like to invite Dr. KITAGAWA Masahiro, professor at Osaka University and the program director of Moonshot Goal 6, to give his opening remarks. Dr. Kitagawa, over to you.
Hello, everyone. I'm Kitagawa Masahiro, program director of Moonshot Goal 6. I'm sorry about that. My photo is not currently available. Later, I'll fix it. Thank you very much for taking time out of your busy schedule to join us today. The Moonshot Research and Development Program has set ambitious research goals to be achieved by 2050. And today, we will explore Goal 6. It is led by me and aims to realize a fault-tolerant universal quantum computer that will revolutionize economy, industry, and security by 2050. In other words, a universal quantum computer that will dramatically benefit our society. In this symposium, we would like to introduce Moonshot Goal 6 to a variety of stakeholders, including international universities and companies interested in collaboration. We hope you find it informative and useful. Thank you again for joining us.
Thank you very much, Dr. Kitagawa. Next, I would like to invite Mr. INOUE Shinji, the Minister of State for Science and Technology Policy, to give his opening remarks by video.
皆さん、こんにちは。科学技術政策担当大臣の井上真司です。本日、ムーンショット型研究開発制度を推進するためのイベントを開催できますことを大変喜ばしく思います。また、新型コロナ感染症によりさまざまな制約がある中でも、関係者の皆様が精力的に本制度の運営に取り組んでいただいていることに心から敬意を表します。この制度は超高齢化社会や地球温暖化問題など未来社会が直面する重要な課題に対し、人々を魅了する野心的な目標を国が設定し、1000億円以上の予算を投じて、目標達成に向けて挑戦的な研究開発を推進するものです。最終的には、我が国発の破壊的イノベーションの創出により、それぞれの目標を達成し、人類社会の課題を解決することを通じて、未来の人々の幸福、いわゆるヒューマンウェルビーイングを実現することを目指しております。ムーンショット目標は、未来社会を展望し、困難であるものの、実現すれば大きなインパクトが期待される社会課題を対象として設定したものです。いずれも極めて困難でチャレンジングな目標ですが、プロジェクトマネージャーをはじめとする研究者の皆様には、失敗を恐れることなく、現在の価値観にとらわれずに、大胆な発想で果敢にチャレンジをしていただきたく存じます。プログラムディレクターの皆様は、研究者たちが思う存分に挑戦的な研究開発に打ち込み、そして仮に失敗したとしても、それを教訓にして次の成功につなげられるような環境づくり、雰囲気づくりをしていただきたく存じます。 国としても関係府省がしっかりと連携しつつ、研究開発から社会実装まであらゆる段階で研究者の皆様が最大の成果を上げられるように全力でサポートしてまいります。チャレンジングな目標を達成していくためには、多くの人々が同じ目標の達成に向けて組織や分野を超えて協力し、お互いの強みを持ち寄って共に困難を克服する共同のキーワードが重要となります。ここで3つの共同の考え方を皆様と共有したいと思います。1つ目は、プロジェクトマネージャー同士の共同です。これから目標ごとにプロジェクトマネージャーたちが同じ目標に向けて日々研究開発に励んでいくこととなります。また、目標や分野は異なっても、同じビジョンを持つ仲間がいるかもしれません。この仲間たちが協力して、時には切磋琢磨しながら、目標達成に向けて困難を克服していくことが重要です。2つ目は、社会、産業界との共同です。2050年、もしくは2040年の目標達成時期までには、研究成果を必ず社会実装しなくてはなりません。このため、今の段階から社会実装を見据えて、社会・産業界と積極的に協働していくことが必要となります。また、新しい技術を社会実装していくためには、倫理、法令、社会の課題、いわゆる LC についても、関係者が粘り強く議論しながら解決していくことが重要です。国としても、行政の立場から皆様の研究成果が円滑に社会実装できるよう、制度改革や制度づくりに尽力してまいります。3つ目は、国際社会との協働です。ムーンショット目標の多くは、未来社会の人類が直面する世界共通の課題を取り上げています。地球上の人類が同じ月を見ているように、海外諸国も同じ目標を見ているはずです。こうした同じ目標を目指す海外の研究者たちと積極的に連携をしながら、地球規模で研究成果を展開していくことが重要です。以上、3つの共同の考え方を紹介しました。この場には、本事業に参加する研究者とともに、国内外、産学官のさまざまなお立場の方にも参加していただいていることと思います。本イベントがより多くの参加者の皆様の共同を創出、加速する場となりますことを期待しております。組織や分野、国境を越えて同じ目標を目指す仲間として、皆様と共にお互いの強みを持ち寄りながら、目標達成に向けて一緒に取り組んでいただけましたら、私としても心から嬉しく思います。最後に、皆様のご活躍が将来のムーンショット目標の達成につながり、本制度の最終目標である未来の人々の幸福、ヒューマンウェルビーイングが実現されることを祈りまして、私の挨拶とさせていただきます。どうぞよろしくお願いいたします。
Thank you very much, Mr. INOUE. Now, let us move on to our keynote speeches. I would like to remind our audience, if you have any questions for our speakers, including our keynote speakers, please put them in Zoom's Q&A box. Now, to introduce our keynote speakers, I would like to hand back to Dr. Kitagawa.
Thank you. First, let me introduce Dr. Charles Tahan from the White House Office of Science and Technology Policy, OSTP. Dr. Tahan earned a PhD in physics at the University of Wisconsin-Madison in 2005. From 2005 to 2007, he was an NSF Distinguished International Postdoctoral Research Fellow at the University of Cambridge, UK, the Center for Quantum Computing Technology, Australia, and the University of Tokyo, Japan. He served as Chief Technical Consultant for Quantum Information Science and Technology programs in DARPA's Microsystems Technology Office, MTO, from 2007 to 9. He is on detail to OSTP from the Laboratory for Physical Sciences, LPS, where he enrolled as Technical Director, Technical Lead, and Chief Scientist. Dr. Tahan is Assistant Director for Quantum Information Science and the Director of the National Quantum Coordination Office, NQCO, White House Office of Science and Technology Policy, OSTP. Dr. Tahan, over to you.
All right, thank you for that great introduction. And it's a real honor to be here today at this really amazing Moonshot program. Really terrific goal. And I've learned already a little bit about all the hubs and the goals of each of them. It's an amazing program. So today I'm just going to tell you a little bit about what we're doing in the United States and as far as our strategy for quantum information science goes, and give you a little context about how US science funding works and what we are doing to push the field forward, including collaboration, across the globe. So I'm going to share my slides and hope that they work. So as I was introduced, I'm Charlie from OSTP. The first thing I like to start off with in presentations like this is just reminding everybody why we're here. I think we all are on the line because we believe that quantum information science and technology will impact our future prosperity. And when it's already happening a little bit, and when it happens in a really big way is up to us, in many different fields, quantum computing, quantum sensing, quantum networking, and foundational physics in like quantum simulators. And all these things are interrelated. And I think the question we ask ourselves is, how do we devote the resources we have to getting to these results, these benefits of society faster? Now, the US, you have to remember, has a very federal approach to science funding. That means there's a lot of different organizations within the government and the private sector, all marching to their own beat to push science funding forward. So there's the Executive Office of the President, where I work, in the Office of Science and Technology Policy. There are other institutions within the EOP that advise the president, such as the Budget Office, the PCAST, which are a select group of outside advisors. The President's Office makes recommendations to Congress, who also has their own ideas about funding in science, and the agencies too make their own recommendations. So there's a cycle here where the three bodies across the government work together to decide on where to put funding. In addition to that, we have many different agencies who do their own funding. They have their own missions, their own models of funding, very different timelines, some short-term, some long-term, some very big-scale funding, some very broad and shallow funding. All those agencies have their own missions, and this creates a very federal or heterogeneous model for funding that's, over the last 7 years has been very successful and very robust. So when one agency, for example, gets interested in and not interested in quantum computing, for example, another may take it up. And so if you look back over the last 30 years, there's been in total a sustained growing investment in quantum information science. And within the White House also, there are a few unique bodies called National Coordination Offices. Quantum happens to be one of them, one of the newest, which try to coordinate massive initiatives like the National Quantum Initiative across all the agencies, and also with the private sector and academia. Okay, so if you look back 2 or 3 years, as quantum has been funded and the agencies have been working together very strongly for the last 20, 25 years at least. But 3 or 4 years ago, industry also started to play a very large role. And this spurred a need to coordinate even more. And the 13 or so agencies in the US who fund or care about the outcome of quantum technology came together to write a national strategic overview. What are the high-level policy goals that the government should do? And about the same time, Congress passed the National Quantum Initiative Act, which was passed in 2018. This formally created a subcommittee within the White House, the Subcommittee on Quantum Information Science, to coordinate across the interagencies. It created the National Quantum Coordination Office, which I'm the director of. It legislated new quantum information science research centers across the country, and it created an advisory committee and so on. So these are the mechanisms that the US uses to coordinate and to drive research agendas forward. So what's in our strategy at a high level? It really revolves around 6 high-level policy goals. First, take a science-first approach. Second, invest in the right kind of infrastructure to drive to those hard technical challenges that you should address first. Build the workforce that we'll need now and in the future as this field grows. Nurture this nascent quantum industry that exists already and we hope to continue to see grow over time. Balance the economic and the national security implications of quantum, because there definitely are economic and national security implications of this technology. And then continue to cooperate globally with like-minded countries, because it really is a global endeavor. It always has been, and we move faster together. So when we did this about 2 years ago, we released our strategy, the National Quantum Initiative Act passed. We asked the community, the scientific community in the US, well, did we get it right? Did we miss anything in our strategy? What else should we be doing? And we got hundreds and hundreds of pages of responses. And in addition to that, all these agencies who are planning new quantum programs held workshops. There were about 30 workshops held within a year-long period. So we took all that data and we put it into a report called a Quantum Frontiers Report, where you can really find the grand challenge technical questions that the community was telling us, you should really work on these first. Before you go off and lay a lot of dark fiber for the quantum network or do other infrastructure projects, solve these hard technical challenges first. And if you do that, that will guide you on the next level of technology development. So for example, these could be, work on the material science challenges that we know we need to solve to make qubits better for a quantum computer. But they could also be, well, find an application, to drive investment in quantum networking or large-scale quantum computing. Find the applications that would justify further investment. So those are just a few examples, but that's sort of how we think about what we should be focusing our researches on now. I want to say that the National Quantum Initiative Act, if you read the law, specifies 3 agencies in particular: the Department of Energy, the National Science Foundation, and the National Institute of Standards and Technology. But there's a much broader ecosystem even within the government. The Department of Defense does a tremendous amount of fundamental research funding in the US. It's almost like a country in itself. There's DARPA, of course, there's the DoD labs, the DoD funding agencies. They all fund quantum and have done so for the last 2 or 3 decades. Then there's the intelligence community labs, IARPA, which is an intelligence version of DARPA, the LPS. They also have funded quantum for a long time because there's a realization that this technology could be disruptive for information technologies, and you really needed to understand it. And these are synergistic with industry and academia who support and do the research and translate the research to commercial use for the benefit of society. And so just to give you an example of, in quantum computing especially, since the early 1990s, when some of the first papers around quantum algorithms and quantum error correction came out, there's been a sustained and large investments of programs across the government, but especially DARPA, IARPA, NIST, in helping evolve this technology. So you may see, news articles where company X or Y, seemingly overnight has gone to 50 qubit quantum computers. Well, that is after 20 years of sustained hard investments by the government to create the core devices and the core research learning that allowed that integration to happen after the fact. And you can see that in all these technologies, in all these programs that were developed. This is just a small sample of the programs that have been run in all these different organizations and all these different models to help drive the field forward over time. So when we say science first, we really mean that. Not that we don't want to see the technology advance, not that we're not pushing the technology forward, but if you want the technology to move as fast as possible, you solve the hardest problem first. That's probably the best way to know that you're not wasting your time, right? And at the same time, you don't want to put all your eggs in one basket because it's still a very early and nascent technology. You want to leave plenty of room for exploration so that you can disrupt yourself and find the new opportunity that will make your life easier to get the practical benefit. So within the White House, we have a subcommittee. Within the subcommittee, we have working groups. The most important one is the science working group, which works across all the technical leads and program managers in the agencies to come together and decide on, negotiate and argue about policy that would affect how we invest in science. And so I'm going to just give you a few examples of that. Probably the best example is quantum networking. Maybe the earliest proposed application, quantum key distribution of quantum information technology, but still I would argue the most immature of the three, computing, sensing, and networking, because while there is a clear classical approach to securing quantum communication, that's post-quantum cryptography, there isn't a clear driver for an application. There's not a clear application for building a large quantum network. And we know in the long term, we would love to be able to hook up quantum computers together. And we expect that if we hook up quantum sensors together quantum mechanically, the whole system will get better. But there's still a lot of questions about how to do that, how to do it right, and what you would need, how big a network you would need, how good should it be, and what you would do with it. What are the real application spaces for a quantum network? So it's really important, I think, to look at quantum networking first across the agencies, bring all the technical experts together, and prioritize what we should do first. And for example, invest in the core component technologies like transducers with high fidelity, build the right size networks to answer the science questions first, as opposed to building something unnecessarily large that doesn't teach you anything more, and so you might go down a wrong path for too long. So quantum networking is a great example of getting the science first, and then investing. And on the flip side, quantum sensors, which promise probably the earliest deployment, and if you call atomic clocks quantum information technology devices, we're already using them in a lot of different fields. For quantum sensing, the question really is, how do we get concepts and ideas out of the lab and fielded? And how can we do that as fast as possible? What are the roadblocks to doing that? Infrastructure, I mentioned that there's new DOE and NSF centers. There's 8 new centers. We expect a few more from NSF. There are also DOD centers that have been designated, QIS research centers. So in total, there's almost a dozen with more to come. The budgets of these are fairly large. The DOE labs are $25 million a year each, funding a lot of students and graduate students to pursue, across the board, quantum computing, sensing, networking, and enabling technology. And if you just look at the list right now, you see there's a computing and sensing and networking center at NSF. They're specialized, whereas the DoD labs, which are much bigger, really cover multiple technologies in each lab. And although there's a lead organization for each center, these represent a very hub and spoke model. There's a lot of different principal investigators and universities and companies working on each of these teams. So this represents thousands of principal investigators and many, many more students. So we don't have the people to fill all these labs, let alone the industry, let alone the government. So there's a real workforce need now, and we recognize that. And the key element of our strategy is how to not only increase the pipeline of talents, but get less people leave science and STEM, science, technology, education, and more to choose this as a career. So one, certainly all these centers are going to generate a lot of graduate students in the next few years, which is going to be fantastic. But a key missing piece originally was, well, what are we doing about high school? What are we doing about kindergarten through 12th grade education? So we were partnered with the National Science Foundation to launch the Q12 Education Partnership, which is very much a government industry partnership, working with the companies, helping them work together to translate educational material at a national scale and really globally, make it available to the community to try to educate more people, to get every person we can, because we really don't have the luxury to be exclusive here. We need to be inclusive and get as many people to realize that they can contribute to this new field. Educate them, inspire them, get them experiences in companies, in national labs, show them that they can contribute, that they have unique skills that can contribute, and then ensure that they have good careers. That's the key thing. People make rational choices. They're going to want to do things that give them a good career. And I think quantum and related technologies will do that. We're really confident of that. We need to get that message out. So I've talked about science, workforce. A key element to quantum information technology is that it's not just the science. This is a technology we expect will have economic benefits. We expect it will have national security impact as well. The first main application for a quantum computer that had exponential speed up was factoring numbers, breaking cryptography. So there are clear economic and security implications. You have to take that into account as you do investments. You have to protect the investments you're making, work with people you trust, and have a venue to talk about how you fund this kind of science and technology development across the government. So we have a subcommittee completely dedicated to that, talking about the economic and national security implications of quantum and how to protect the research environment, maintain our scientific integrity as this field grows. And that leads to our industry. So we're very hopeful of this technology. There's a lot of enthusiasm right now, and if you read the popular press, there's a tremendous amount of enthusiasm for quantum computing. Large investments coming from the venture capital community, from big companies. Many small companies started. One of the NQI acts, one of the National Quantum Initiative acts, asks was to form an industry consortium, and the Quantum Economic Development Consortium, stood up by NIST, is the US's Quantum Industry Consortium. It already has 140 companies signed up, another 40 or 50 professional societies and universities. So quite a big group now. And their main focus is to think about, well, what's needed for the supply chain? What are the missing pieces here that we will need in the future? And again, just focusing on security is a key aspect of this, and how do we protect and help the industry grow? Likewise, it's really key. Quantum has always been a global endeavor. The ideas for this field trace back to the 1980s, and they come from, all across the world. And we are very clear that in order for this field to be successful, we need to not only invest in it here, we need to grow the marketplace of ideas and talent and industry, with all our partners in like-minded countries. And it's much better to move faster together and be first together than to be second or third apart. So that's really our philosophy. And that was codified in the US Tokyo Statement on Quantum Cooperation that was signed back in February 2019, the first such cooperation agreement that the US signed. And it's just very simple. This is what we believe in terms of what makes a healthy scientific environment. Here's how we should interact. So we very much look forward to continuing that as Japan stands up your new innovation hubs and quantum initiative yourself. So there's a lot of opportunities here, workshops. We love to see more people exchange, students and postdocs and professors on sabbatical coming both directions. We have the industry consortium. I think there's a lot of interest in industry engagement. And of course, the agencies themselves, as they fund things, are always looking for potentials to collaborate. So just looking forward in the last minute here, what I'm thinking about over the next year is, how does quantum information affect and interface with society? And how can we further augment our national strategy? What's missing over what we've done so far? How do we continue to accelerate our competitiveness worldwide? How can we help in this nascent industry? And how can we ensure that quantum information science and technology benefits all Americans? There's tremendous opportunity here for new jobs, for technologies that benefit society, but how do we make sure that we are giving these opportunities to everybody as much as possible? That's the challenge, and that's the opportunity we face. So that's it. That's all I had to say. You can find more at quantum.gov. We try to launch all our new initiatives and reports on this website. And thank you to the other people in the National Quantum Coordination Office who helped make all this coordination happen. Thank you.
Thank you very much, Dr. Tahan. I quite agree that the exchange of young researchers will be a very promising international cooperation between the United States and Japan. I'd like to take one question from a Q&A box. This is a question from, I guess, Koashi-san, PM. The fault-tolerant universal quantum computers, our goal is for a very long-term goal. It may take 30 years, and it's beyond the ordinary patent, beyond the patent validity period. What do you think about that sort of long-term investment and patent issues? Do the United States have some strategy on that sort of long-term patent issues?
Well, I mean, I may not be the best expert here because, I started my graduate degree in quantum information science back in 2020, and I have a lot of patents that are now expired. So I didn't make out very well. But I think the key is, creating value. At the end of the day, you're creating value. You're doing something that can't be done with classical computing. And maybe there'll be money from patents, but I think the fundamental thing is, can you create something that actually has value to society, and that will lead to wealth generation. I mean, that's my fundamental philosophy on economic and why you do things. And so there'll be new opportunities as quantum computers are developed. I don't think it's worth worrying about patent law, frankly. I think.
Yeah, thank you very much.
Maybe it'll be sooner, right? I mean,
yeah,
it doesn't have to be 30 years. It could be sooner, right?
Yeah, we hope.
We don't know.
We hope so. Nobody knows.
Yeah.
Thank you very much, Dr. Tahan.
Thank you. Appreciate it.
Next, I'd like to introduce the next keynote speaker. Dr. John Preskill is a Richard P. Feynman Professor of Theoretical Physics at the California Institute of Technology and Director of the Institute for Quantum Information and Matter at Caltech. Dr. Preskill began his career in particle physics and cosmology, but now his main research area is quantum information science. He's interested in how to build and use quantum computers, and in how our deepening understanding of quantum information can illuminate issues in fundamental physics. Dr. Preskill, over to you.
All right, thank you very much for the kind introduction. I'm excited about the Moonshot program and honored to be here. I think many of us believe that quantum technology is going to have a big positive impact on the world in the future, but we don't know how long it will take to fulfill our aspirations for the field. So I'm pleased that in the Moonshot program, you're taking a long-term view concerning the scientific and technical challenges that we're facing. We are confident that in the long run, quantum computing will be very impactful. That belief rests on two fundamental ideas. quantum complexity, our basis for thinking that quantum computing will be powerful, and quantum error correction, our basis for believing that we can eventually scale up quantum computers to large systems that can solve very hard problems. When we speak of quantum complexity, what we often have in mind is the extravagant complexity of describing, using ordinary classical information, highly entangled states of many qubits. For just a few hundred qubits, it's impossible to write down a complete description with classical information because the complexity grows exponentially with the number of qubits. Now, that by itself doesn't necessarily mean that by processing qubits, we can do things that would be useful. But we do have several reasons for thinking that quantum computing is powerful. For one, we know of some problems which we believe are hard to solve classically, which theoretically quantum computers would be able to solve efficiently. Factoring large numbers is the best known example. The theoretical computer scientists have given arguments based on plausible assumptions that one can do a rather modest size quantum computation and then measure all the qubits, and that by doing so, we're sampling from a probability distribution that we can sample from efficiently by any classical means. But perhaps most tellingly, we just don't know how, in general, to simulate with a classical computer efficiently what a quantum computer does. And that's not for lack of trying. Physicists and chemists have tried for decades to come up with better algorithms for simulating complex quantum systems, but still, in hard instances, the best algorithms that we have scale exponentially with the problem size. So we believe that there are problems which are too hard to solve with our classical computers now and in the future, which can be easily solved by future quantum computers. We have a strong incentive to understand better what are these problems that are classically hard and quantumly easy. And we've learned a lot about that over the past 25 years. I think we still have a great deal more to learn. But for a physicist, there's a natural place to look for such problems. We believe that with a quantum computer, we could efficiently simulate any process that occurs in nature. We don't think that's true of our classical computers, which can't efficiently simulate very highly entangled matter. So with quantum computers, we should be able to probe more deeply into the properties of complex molecules and novel materials, as well as explore fundamental physics in unprecedented ways. But it's been 40 years now since Richard Feynman first suggested the idea of solving hard problems with quantum computers, and we're just now getting to the point where the hardware is sufficiently advanced that quantum computers can start to do interesting things. So evidently, building a quantum computer is hard. It's hard because we want a device which can simultaneously satisfy a set of criteria which are nearly incompatible. We want qubits to interact strongly with one another so we can rapidly process the information that they encode. We don't want qubits to interact with the environment, which would damage the quantum information we're trying to process. But we do want to be able to control the qubits from outside and eventually read them out to find the answer to a computational problem. So it's only through some decades of improvements in qubit design, control methods, fabrication, and so on, that we've gotten as far as we have. And there are a variety of hardware approaches that are under development, reflected in the thrusts of the Moonshot program. And it's important that we continue for the time being to advance these different complementary hardware approaches. We really don't have a good understanding at this stage of what technology will have ultimately the best prospects for scaling up to large systems. And it may be that different technologies find different niche applications, or that a hybrid of technologies will turn out to be the best strategy going forward. Now, when I said that we don't want qubits to interact with the environment, the reason for that is the formidable enemy of the quantum computer, decoherence. Quantum information has the inconvenient property that we can't observe it without disturbing it in some uncontrollable way. So if we want to process quantum information reliably, we have to keep it nearly perfectly isolated from the outside world. We can't allow information to leak to the outside world, and that's very difficult because our hardware is far from perfect, but we've understood in principle that there's a software solution to that problem, the idea of quantum error correction. The essence of the idea being that if we want to protect quantum information from damaging interactions with the environment, then we should encode it in a highly entangled form in a system with many parts, so that when the environment interacts with those parts one at a time, it can't see the encoded information, can't acquire information about what the encoded state is, and therefore can't damage it. And we've understood in principle how to efficiently process quantum information that's encoded in this highly entangled protected form. Really, it's one of the most remarkable things that we know about the difference between the classical and quantum world, that in general, we don't expect that classical systems can simulate what quantum systems do efficiently. There's a strong incentive to validate that in the laboratory to the extent that we can. And in fact, in 2019, the Google Quantum Group, with some fanfare, proclaimed that they had achieved the milestone of quantum computational supremacy, that is, performing a task with a quantum device that would be very hard to perform with a classical system. What the Google group did is they constructed, with superconducting technology, a quantum computer with 53 working qubits laid out in a two-dimensional array, such that neighboring qubits can be acted upon by entangling two-qubit operations. And they performed up to 20 layers of such entangling two-qubit gates before reading out the qubits and obtaining a classical string of 53 bits. Now, the device is quite noisy, so that when they perform that procedure, they get the right answer only about 1 out of 500 times, but they can perform the same computation over and over again, millions of times in just a few minutes to get some statistically useful signal. But if we asked a classical computer to accurately predict what Sycamore finds by that procedure, that would be a very hard computation, even for the most powerful existing supercomputers operating according to classical digital technology. And furthermore, the cost of doing that classical simulation continues to grow exponentially as we increase the number of qubits. So arguably, the quantum computing technology has reached the point where quantum computers may be capable of doing things that we can't do with classical devices, which opens the possibility of finding real applications. It's useful to have a word for the era that's opening up of quantum information processing. The word NISQ has caught on. It means noisy intermediate scale quantum. Intermediate scale to indicate that we're talking about devices of sufficient size, say more than 50 qubits, such that it's very difficult by brute force to simulate with a classical computer what the quantum computer does. But noisy to remind us that these devices are not error corrected, and the noise is a serious limitation on their computational power. For physicists, NISQ is exciting. It means that we have a new tool for exploring the physics of many interacting qubits in a regime that's never been experimentally accessible before. And it may be that NISQ technology will have practical applications of broader interest, but we're not really sure at this stage whether that's true. We should really think of NISQ as a step towards powerful quantum technologies that we're hoping to develop in the future. I think there's reason to be confident that future quantum computers will have a transformative effect on society, but we're still not sure how long it'll take to get there. There is a kind of emerging paradigm of at least one way in which we might attempt to solve hard problems with quantum devices, a kind of hybrid quantum classical scheme. in which we make heavy use of our powerful classical computers and then try to boost their power with a kind of quantum coprocessor. That type of scheme could be used to attempt to find approximate solutions to hard optimization problems. Should we expect that with NIST technology, we'll be able to solve optimization problems which are beyond the reach of what we can do with the best classical hardware, running the best algorithms for solving the same problems? Well, we don't really know. We'll have to try it and see how well it works and learn more as we experiment with the technology. But that's really a lot to ask because the classical methods are well honed after decades of development, and these NIST processors are just becoming available for the first time now. I think we can be more hopeful that over the next 5 or 10 years, we can advance science using quantum computers and quantum simulators to study the dynamics of many interacting qubits and, for example, advance our understanding of quantum chaos. And this can be done either in a digital mode, using, that is, circuit-based quantum computers, or with programmable analog quantum simulators. Both approaches are important to pursue, but realistically, we'll really, most likely, in the next few years, be setting the stage for more impactful simulations of complex quantum systems that we're hoping to do in the future. So in the long run, what types of applications might we hope to run on quantum computers? Well, somewhat optimistically, we can envision applications to chemistry, materials, and optimization requiring only a few hundred qubits, but that's under the assumption that the qubits are perfect, that we can perform quantum operations with perfect fidelity on those qubits. And we're far from being able to do that. More realistically, if we include the overhead costs of doing quantum error correction, even if we have quantum hardware that's somewhat more reliable than what we currently have in multi-qubit devices, it's likely to take millions of physical qubits to run some of these applications in the regime where they can really surpass the best classical computers. So just to be clear, what I'm emphasizing is that currently, actually, 2-qubit gates typically have error rates in multi-qubit devices at about the 1% level. We can envision improving that to something like 0.1%, perhaps, in the not too distant future. But even then, in order to run these applications, we need rather deep circuits, which means lots of gates, which means a much higher accuracy is needed per 2-qubit gate in order to perform the application reliably. Let's say for applications to materials, we might want a error rate per protected gate at the 10 to the minus 8 or 10 to the minus 9 level. And even with the best error correction schemes that we're currently aware of, that's probably going to require hundreds or thousands of physical qubits per protected logical qubit. And so that gets very costly. It means we have to make a big leap from where we're likely to be in the next few years with maybe hundreds of physical qubits to millions of physical qubits to see some of these applications come to fruition. In the meantime, if we could improve gate error rates significantly, that would be very helpful. It would make NIST technology more powerful, and it would also mean lowering the overhead costs of future fault-tolerant quantum computers. This is very hard to do. There are a number of approaches that one can try. An old idea is topological quantum computing based on encoding qubits in a topological material. So there's some physical protection against noise. But there are other ways of trying to incorporate some protection against noise into the hardware itself, of which I've indicated a few here. All of these are still in their rather early stages, and we don't know how well they'll pan out. but it's important to continue to pursue them because big improvements in gate error rates would bring us much closer to realizing useful applications of quantum computation. Part of making those improvements involves materials issues. That takes a lot of time and resources, and the timescale for progress can be difficult to predict. And at any rate, we need more than just better materials. We need innovative ideas about how to make use of those materials in better qubit designs. What will the long-term impact of all this be? Well, nobody knows that. Nor can we be expected to very well imagine how quantum computing is going to change the world. But of the applications we currently most clearly foresee, what we can imagine having the biggest impact on society are the applications to chemistry and materials, which could improve human health and agriculture, energy production, and the sustainability of the planet, and so on. But it won't be easy, and it won't be fast. In order to realize our aspirations for the field, that will require a sustained effort over an extended period. So I'm glad to see that that's exactly what you intend to do in the Moonshot program, to have realistic timescales in mind for achieving the quite daunting goal of a scalable fault-tolerant quantum computer, and I wish you luck. Thanks a lot for listening.
Thank you very much, Dr. Preskill, for our encouraging and inspiring talk. What is the okay? I would like to ask actually two questions to you. One is, actually the number of qubits, the increasing number of qubits is daunting, and I think it's very difficult. What is your view? What is the most difficult part to accomplish fault tolerance, quantum fault tolerance? That is one question. And another question is, what is your advice to these challenges targeting fault-tolerant quantum computer in 30 years, these 7 program managers, project managers?
The first question is, what is the most difficult part? Well, it's all really, really difficult. I think, as I said, one thing that would be very helpful would be better qubit technologies, and in particular, higher fidelity 2-qubit gates that would make the overhead cost of fault tolerance significantly less. Even so, we're going to have to scale up some of these platforms to a number of physical qubits, which will create new challenges. Now, partly that's an engineering challenge, but I think it's really more fundamental than that, to think of the best ways. Probably it'll mean some sort of modular design with a number of modular processors which are somehow wired together, and that involves some of the same challenges that Charlie Tahan mentioned in his remarks about networking. How to do transduction and how to do reliable transmission of quantum information and so on. So of course it's interesting, and it wasn't the main theme of my talk, but is worth emphasizing that some of the technological challenges we're facing in trying to scale up quantum computing have much in common with some of the other ramifications of quantum information science, including in networking and sensing.
Thank you. And what is your advice to these challenges?
Well, actually, I thought we heard some good advice earlier in the program about not being afraid to fail. I think we have to be bold, and I think the potential of the Moonshot program to have a huge influence on the field is not to do what everybody else is doing incrementally better, but to think about what kinds of advances would really be transformative, and to think about different approaches to scaling up and improving gate fidelities than the obvious ones. And of course, that's really hard and it's not always going to succeed, but it could, if successful, really transform our view of the timescale for quantum computing to have a big impact on the world.
Well, thank you very much again, Dr. Preskill. And thank you, Dr. Tahan, once again for your excellent keynote speeches. It is a great pleasure and honor to have you with us. That concludes the keynote session. So now, please let me give a brief overview of Moonshot Goal 6. Is it okay? Okay, quantum computers are expected to outperform supercomputers due to the unique properties of quantum mechanics. However, the quantum computers currently available are difficult to perform large-scale calculations because of the quantum errors. Moonshot Goal 6 aims to overcome the quantum error problem and realize a fault-tolerant universal quantum computer that will revolutionize our economy, industry, and security by 2050. Today, at the start of the 7 R&D projects under the Moonshot Goal 6, we would like to share our dreams and challenges with international community. So let me briefly introduce myself. I'm a program director, KITAGAWA Masahiro, and the professor of Graduate School of Engineering Science, Osaka University, and the director of Center for Quantum Information and Quantum Biology. I was originally a theorist in quantum optics and quantum information, working on squeezing or entanglement of spins as well as photons at NTT Basic Research Laboratories in 80s and 90s. After I moved to Osaka University, I have worked on a series of quantum computer projects and recently founded the Center for Quantum Information and Quantum Biology. The Moonshot is a bold new program for creating disruptive innovation decided by Council for Science, Technology, and Innovation in Japan. We will tackle the challenges facing future society through ambitious goal-oriented research projects, leaping beyond the limits of conventional technology without fear of failure. CSTI has set the 7 ambitious goals. The one is realization of a society in which human beings can be free from limitations of body, brain, space, and time. The second is ultra-early disease prediction and intervention. The third is AI robots. And fourth is sustainable resource circulation. And fifth is sustainable global food supply. And sixth is our fault-tolerant universal quantum computer. And seventh is overcome major disease by 2040. Okay, we aim to realize a society in which science, industry, economy, and security have dramatically advanced, and global social issues and difficult problems are solved with the power of quantum computers. As quantum computers can calculate highly entangled quantum states as they are, it is expected that the accuracy of quantum chemistry calculations will improve dramatically, and the functions of catalysts and enzymes will be elucidated. As a result, the efficiency of energy and material utilization in industry will improve dramatically, leading to the solution of energy, resource, and environmental problems. For example, a few percent of entire energy consumption is currently used for the industrial production of ammonia, the raw material for nitrogen fertilizer. If a biological nitrogen fixation by the enzyme nitrogenase is elucidated by quantum chemical calculations on quantum computer and is artificially mimicked, energy saving of orders of magnitude will be realized. Similarly, if we can mimic the photosynthesis of plants, we can reduce carbon dioxide and help solve global warming. However, the quantum computers realized today have about only 50 to 100 qubits and are vulnerable to quantum errors and cannot perform large-scale calculations. Such a quantum computer is called Noisy Intermediate Scale Quantum Computer, NISQ for short. In 2019, it was shown that simulating the operation of NISQ with a supercomputer would take a long calculation time and in a sense would exceed the capacity of the supercomputer. This is called quantum supremacy. Large-scale quantum chemistry calculations to elucidate nitrogen fixation or photosynthesis require an ideal quantum computer without errors. That is a fault-tolerant quantum computer that performs calculations while correcting quantum errors. To achieve this, it is necessary to significantly increase the number of qubits to provide redundancy, perform quantum error correction, and lower the error probability below the fault-tolerant threshold. However, increasing the number of qubits can be physically constrained. For example, the number of ions aligned in the trap is limited. The number of superconducting qubits accommodated in a dilution refrigerator is limited. Therefore, it is also necessary to connect multiple small to medium-sized quantum computers by quantum communication network to operate as a larger scale quantum computer. Since the strength and topology of the coupling among qubits depend on the physical system, it is necessary to find a suitable quantum error correction scheme and make the fault-tolerant threshold as high as possible. The error probability of the quantum gate should be reduced below the threshold. Project managers have been recruited in 3 categories: quantum computer hardware, quantum communication networks, and Therian software. We had adopted 7 projects for hardware, superconducting, ion, photon, and silicon, 2 communication networks, and 1 Therian software. This is our portfolio. Hardware projects work in competition with each other. Quantum network projects work on quantum interfaces, quantum memories, and quantum communications for distributed quantum computers. Theory and software project works on quantum error correction and quantum fault tolerance over distributed quantum computers. Projects in different categories work in collaboration. The government of Japan will invest 100 million USD in the first 5 years. It is very encouraging that the government has made a clear commitment to fault-tolerant quantum computers. Thank you very much for your kind attention. Now we will invite ambitious project managers to introduce their projects. Let me move on to the project overview presented by the project managers. The first project manager is Dr. Yamamoto Tsuyoshi from NEC Corporation. Dr. Yamamoto, over to you.
Thank you very much. Good morning and good evening. I'm Tsuyoshi Yamamoto from NEC Corporation. Today I will introduce our project development of integration technologies for superconducting quantum circuits. Here is outline of my talk. First, I will start with a brief introduction of superconducting quantum computer and its technological challenges. Then I will explain what we will try in this project and I will briefly introduce all our research themes. But today, I will pick one subject of cryoelectronics and go slightly more details into it. The first superconducting qubit. In this Moonshot program for Goal 6, there are different hardware categories which deal with different physical systems to implement scalable qubits. In my project, which I will introduce now, we focus on superconducting qubit. It is an electric circuit made of superconductor and Josephson junctions. Essentially, it is a nonlinear oscillator with typical resonance frequency of around 5 gigahertz and is operated at 10 millikelvin in a dilution refrigerator. And it is fabricated by using photolithography, which makes the integration relatively easy. Also, it has a high degree of design flexibility. But they come at the expense of relatively short decoherence time and non-uniformity, which are shortcomings compared to other physical systems such as trapped ions and photons. But presently, superconducting system is one of the leading platforms for the quantum information processor, as is demonstrated in this famous quantum supremacy experiment from Google team using 53 qubits. And as the paper says, one of the biggest targets in the current superconducting qubit research field is to demonstrate NISQ applications using probably 50 to 100 qubits without error correction. But in this Moonshot program for Goal 6, the target is a fault-tolerant quantum computer, which is far beyond the NISQ. And from the viewpoint of hardware development, I think there are mainly two big problems to be solved. The first one is that we need a formidably large number of physical qubits. This, of course, depends on many things such as error rates and error correction codes. But one estimate predicts that 10 to the 8th physical qubit is required to run some useful algorithm. And the second one is wiring and electronics. In the superconducting qubit system, as shown here, we need to transmit microwave pulses from room temperature electronics to the qubit, which is located at 10 millikelvin via coaxial cables. And typically, more than one coax line per qubit is required for the control. And bulky microwave components such as amplifiers or isolators are needed for the readout line. And because of the space and cooling power limitations of the refrigerator, current approach is probably not scalable beyond the order of 100 qubits. So at present, there are 6 orders of magnitude gap between manageable and required number of qubits. And thus, we need to increase the number of manageable qubits and to decrease the number of required qubits, both by orders of magnitude in order to realize fault-tolerant quantum computer. The former technologies is, for example, electronics operating at low temperature to reduce the number of cables, high cooling power refrigerator, high density wiring, chip-to-chip interconnections, and so on. And the latter technologies include improving the qubit coherence to improve the gate fidelity and also hardware efficient quantum error correction scheme, such as bosonic calls. And this picture shows kind of a picture of the quantum computer we envision based on those technologies. Basic strategy is to put control and readout electronics as close to the qubit as possible, hopefully at the same temperature as the qubit is located, using cryoelectronics such as single flux quantum circuit and high density wiring, and such as a flip chip bonding, and using higher cooling power refrigerator and better quality superconducting qubits or hardware efficient qubits such as bosonic qubits. In this project, we will develop these technologies. We divide them into 3 categories of first, superconducting qubits for fault-tolerant quantum computing. Second, hardware systems for integrated qubits. And third, electronics for quantum error correction. And hereafter, I will introduce the sub-themes and the corresponding principal investigators for each category. The first category, superconducting qubits for fault-tolerant quantum computing, includes 4 sub-themes. First 2 are mainly about the fabrication of quantum circuits to improve the quality of the device. They will try to establish stable fabrication of long coherence qubit, and they will investigate some novel materials such as tantalum or titanium nitride, or use oxide-free epitaxial Josephson junctions based on niobium nitride. And they are conducted by 5 institutes, and the PIs are me and Kunihiro Hiromata from AIST, Kazuki Koshino from Tokyo Medical and Dental University, and Fumiki Yoshihara from NICT, and Masamitsu Tanaka from Nagoya University. The third theme is also related to fabrication, but the goal is to develop high throughput and high uniformity qubits using immersion exposure instead of conventional E-beam exposure. They will try to develop a qubit fabrication process which is compatible with standard CMOS process using 300mm wafers. This is conducted by Satoru Odate from Nikon Corporation. The fourth theme is study of hardware efficient bosonic qubits using superconducting resonators. This is conducted by 3 institutes and the corresponding PIs, Shiro Saito from NTT Basic Research Laboratories, Atsushi Noguchi from RIKEN, and Jiaosen Tsai from Tokyo University of Sai. The second category, hardware system for integrated qubits, consists of 3 sub-themes. The first one is development of hybrid qubit module, which aims to develop vertically stacked heterogeneous circuit using multi-layer flip chip bonding. This is conducted by Shinichi Yoro's group from RIKEN. And the second theme is to develop a refrigeration system dedicated to superconducting quantum computer. This is conducted by 2 cryogenics expert companies, and the PIs are Masamichi Saito from Albac Cryogenics Inc. and Yuya Fujiwara from Albac Inc. And the third theme is to develop low noise and low power microwave amplifiers based on the superconducting SIS mixers, by which we want to replace HEMT amplifiers commonly used in the present superconducting system. And this is conducted by 2 institutes, and the PIs are Yoshinori Uzawa from the National Astronomical Observatory of Japan and Akira Kawakami from NICT. The third category, electronics for quantum error correction, includes 3 sub-themes. The first one is the study of single flux quantum circuits for control and readout of qubits, which is conducted by Masamitsu Tanaka from Nagoya University. And the second one is the study of cryo-LSI for control and readout of qubits. And this focuses on the low power FPGA based on the solid electrolyte atom switch called nanobridge. And this is conducted by 3 institutes, and the PIs are Munehiro Tada from Nanobridge Semiconductor Inc., Ken Uchida from the University of Tokyo, and Hiroki Ishikuro from Keio University. The third theme is study of digital microwave electronics for control of superconducting quantum computers, which aims to develop scalable and low latency digital microwave electronics for quantum error correction. And this is conducted by Makoto Negoro from Osaka University. In the rest of my talk, I would like to introduce a little more details of the research subject. Since time is limited, I focus on the cryoelectronics of the third category. Again, the aim of the research is to solve hardware bottlenecks, which prevent the which the present typical superconducting qubit system has for scaling up beyond several hundreds of qubits. The bottleneck is I/O bottleneck and the cooling power bottleneck. The I/O bottleneck is a limitation in the number of coaxial cables, which presently we use more than 1 coax line per qubit. The cooling power bottleneck is a limitation of the cooling power of the fridge. As we come closer to the qubit at low temperature, smaller cooling power is available. And the power consumption of the cryoelectronics must be lower, of course, than that. In order to solve these bottlenecks, we combine several power-efficient technologies, such as superconducting single-flux quantum logic circuits and the nanobridge FPGA, and optimize the total cryoelectronics system based on their power consumption and information processing capabilities. For example, SFQ has much lower power consumption and can be operated even at 10 millikelvin. On the other hand, nanobridge FPGA has higher power consumption, but it can perform more complicated processing needed for error correction feedback, for example. So ultimately, we want to replace the present room temperature electronics with that operating near the qubit at low temperature. I will briefly introduce a single flux quantum logic circuit. It is an ultra high-speed digital LSIs using quantized magnetic flux in a superconducting loop. Since it is a zero mass and information carrier and recharge process, which is typically required in the CMOS technology, is not needed, the circuit can operate at extremely high clock speed of 100 gigahertz with extremely low power consumption. And this can be potentially utilized for qubit control, readout, and error correction processing at low temperatures. The technology is well matured, and the Nagoya University group has already demonstrated lots of high-speed digital circuits operating at 4 Kelvin. And these circuits may be directly applicable for the present project, but we will investigate what we can do at qubit temperature, where the cooling power is much more limited. And the circuit optimization for 10 millikelvin operation is the first challenge of the project. Another power efficient technology we use is nanobridge. It is a programmable atomic scale copper wiring formed in a solid electrolyte. It can be used as a non-volatile memory, and FPGA can, based on the nanobridge, has been already commercialized. It has advantages such as low consumption power, radiation tolerant, high density compared to standard CMOS-based FPGAs. And switching operation at low temperature has already been demonstrated. We will try to optimize the device parameters in order to use the FPGA as a low-power digital controller at 4 Kelvin. So by utilizing these technologies, we will try to demonstrate SFQ and nanobridge FPGA-based control and readout electronics operating near the qubit. we will establish ultra-low power SFQ circuit technology for millikelvin temperature. We estimate 100th power reduction compared to that of the conventional 4K design. And using the circuit, we will demonstrate a digital demultiplexer circuit which distribute the qubit control signal to multiple qubits so that we can reduce the number of the quarks lines. And ideally, we want to avoid transmitting the analog microwave readout signals from 10 millikelvin to 4 Kelvin. Therefore, we will also study possibilities of some SFQ-friendly qubit readout scheme. So this is a summary of my talk. In order to realize fault-tolerant superconducting quantum computer, we need to increase the number of manageable qubits and to decrease the number of required qubits, both by orders of magnitude. And in this project, we will develop hardware technologies required for scaling up the circuit of superconducting qubits more than 100 and reducing the hardware complexity. And we will collaborate with the ongoing parallel superconducting qubit project, QEEP, led by Professor Nakamura, which target the 100 qubit circuit for the NISQ application. And so we will collaborate to realize further scale up smoothly. Thank you very much for your attention.
Thank you very much, Dr. Yamamoto. I'd like to ask one question. Okay, your project is a very big project, and in the various aspects are taken care of. What is the most difficult part in your project?
You're asking technological point or management point of view?
Maybe both.
Yeah, so from the technological point of view, I think the readout part is most difficult part. So in order to fully solve this wiring problem, we need to we need to invent some new readout scheme which doesn't rely on the some maybe JPA or microwave amplifiers, circulators, and in a scalable fashion. So we will try to implement that, but yeah, that is of course very difficult, challenging task. And from the management point of view, yeah, so we have many players in the project, and so some people are not from the quantum technology community, but so we want to make close discussion, close collaboration between those quantum and non-quantum participants, and that will probably generate some new ideas, and I want to manage in such a way that it will work smoothly and efficiently.
Oh, thank you very much. I think that we need lots of classical technologies to accomplish quantum fault-tolerant.
Yeah.
Tolerance. Thank you very much. Again, Dr. Yamamoto. I'd like to take, okay, I'd like to proceed. Okay. The next project manager is Dr. Takahashi Hiroki from Okinawa Institute of Science and Technology Graduate University. Dr. Takahashi, over to you.
Thank you very much. I'll just share. All right. I'm Hiroki Takahashi from Okinawa Institute of Science and Technology Graduate University, and then I'm in charge of ion trapping technology in this Moonshot Goal 6 project. So let me just start with some introduction. And so, as is well known, quantum mechanics started with studies of simple atoms, and then our discipline is actually atomic physics. So that's why I'm talking about this. And then at the beginning of 20th century, the Niels Bohr came up an idea of so-called Bohr model, which explains well spectral lines of hydrogen, such as Lyman trees, and so on. And then after that, Schrödinger's and others found out that it's more like waves and then wave functions and so on. And so that means atomic physics has a long history, and it is very well understood, and it's now in the domain of precision science. And it is also well known that the quantum effects can be manifested in isolated atoms. So let me just change the pointer. Sorry. Okay. So if the isolated atoms are such quantum objects, and then so when we make a quantum computer, what if we could line up individual atoms one by one, such as this? And it could be just like a simple recipe for making quantum computers, maybe. And then in this case, each atom works as a qubit. And this is a very simple idea. And then actually, that's what ion trapping just does. And in this video, you can see these white dots, and each one of them is actually a trapped ion. And then, so this is not ions splitting up. It's just we are loading ions one by one, and then we can actually see them individually. Okay, so this is ion trapping, and then I just briefly explain what is ion trapping. What ion trapping is, and then so they are ions. The ions are charged atomic particles, and then why ions and non-neutral atoms? Because they are charged. That means we can manipulate them with electricity, and that's very convenient. And indeed, we can trap them with this kind of device. So by applying voltages to the electrodes, we can trap ions like this in a linear chain, and then they are also trapped in high vacuum. That means they are isolated, and then nothing is around them, and that contributes high coherence of trapped ions. And as you can see, they are almost stopped in vacuum without any residual motion. This is because we have a technique so-called laser cooling, and then we can cool down atoms down to millikelvin and the microkelvin, and then so that's what ion trapping does. In order to utilize this technology for quantum information processing, I'm just going to explain some principles of ion trap quantum information processing. So let's say ions are trapped in a harmonic potential like this, and then each one of them is a qubit. So that means they have two levels, and the two levels have a distinct resonance frequency. Here it's omega naught, and then we can drive them. Sorry. Also, they are connected by a Coulomb interaction between them. So it's like a spring connected these ions, and so that means they move together. So that's a collective motion, and because we can cool this motion down to very low temperature, that means this motion is also quantized, and it gives us components of motion. And then by driving the laser, by driving the ions with lasers, we can create interaction between qubit and these phonons. And And in this case, this qubit interacts with the phonon of the collective mode. And we can also drive another ion and create interaction between this qubit and then collective motion. And in this way, we can create interaction between this ion and that ion. So the qubit interaction can be implemented with this collective phonons, and then this is the basis for two qubit entangling gates such as Dirac-Zohar gate and Moore-Sorensen gates. And the entanglement between ions can be made between arbitrary pairs in the ion chain. So this gives us the possibility of making all-to-all connection in the trapped ions. So this is the principle. And then state-of-the-art of ion trap quantum information processing is as follows. And so basic elements have been demonstrated so far with very high fidelities already. So the single qubit gates has been demonstrated with a fidelity of 99.999%, and the two qubit gates with an error of 0.1%, and then a state preparation and measurement is demonstrated with a similar fidelity. And then notably, the coherence time of trapped ions is very long, could be very long. And for example, this paper demonstrated a coherence time of more than 1 hour. That means it's practically unlimited. And so these elements are very well demonstrated. And then the quantum computers based on ion trapping is actually commercially available with cloud-based services provided by private companies such as IonQ and Honeywell. And then we can ask what's the current issue, and the current issue is the number of qubits. So we need to increase number of qubits. For example, so 13 ions and or 20 ions have been demonstrated. But what's the bottleneck to go more and to go beyond these? And the question is, can we scale up the system to a larger one with the current setup? So that means, can we just increase the number of ions in a single trap indefinitely? So if you think of the consequences when we increase the number of ions in a single trap, actually there are several issues. So one of them is that we have to accommodate increasing Coulomb repulsion between ions. That means we have to lower the frequency, the trapping frequency of the trap. And then because the quantum gates of trapped ions are based on the motion of the ion, that means those gates gets slower and slower. And it also creates motional heating and the trap instability and so on. So that's not good. And also, because the number of sidebands, the motional sidebands in frequency space increases with 3n. And because the frequency itself gets lower, that means the gap between those sidebands gets smaller and smaller, and eventually we get erroneous crosstalk between sidebands, and this just breaks down the entire quantum computer system. So the question, the answer to this question is that so we cannot increase the number of ions indefinitely in a single trap, and there's a probably practical limit of probably 50 to 100 ions. And that means our challenges is increasing ions in a single trap does not work in a long run. So that means we need a technology to connect multiple ion traps. So there are two major strategies to this. So one of them is called the quantum CCD, and it's based on shuttling of physical shuttling of ions between different traps. And the other one is photonic interconnects, and this is based on photonic technology that combines multiple individual ion traps. And then we take on this technology basically, and then our design, the basic design concept is something like this. So in this design, we have ion trap module, and then they are connected with photons. And this gives us a scalability beyond the single trap. But at the same time, we want to have a very good ion trap module, and especially with some novel functionalities in it. So we are going to exploit optical, microwave, photonic degrees of freedom of ions. And so let's look at this ion trap module. So it's very, for our plan, the creating a very good ion trap module is very important. So for this ion trap module, we have to have an efficient ion photon quantum interface in order to make the photonic interconnects possible. And at the same time, we'd like to have a high fidelity fast quantum logic gates in this ion trap module. And also, trapped ions have phononic degrees of freedom, and we want to make use of them for quantum error correction. And all of these have to be supported by fabrication and the characterization of high performance ion traps, and then that technology. And we also work on research and development for cloud quantum computing in the future. And then we allocate different subgroups for each one of these projects. And then I just introduce one by one. So first one is about photonic interconnects, and then that is managed by myself. And then, so in this sub-project, we are going to work on the photonic interface between the ion and then photons. So, and then what we have to do is we have to improve the efficiency of photonic interconnects significantly. And then we believe that it's only possible by cavity QED. So in cavity QED, we put an ion inside an optical cavity, and then the interaction between the ion and the cavity just enhances the efficiency. And then this is based on, so this project is based on the result of strong coupling between an ion and a photon, which was demonstrated recently by ourselves. So, and experimentally, we are going to integrate micro optical cavities in a linear trap. And then, and eventually we want to achieve remote entanglement rate beyond the 10 kilohertz, and that is 2 orders of magnitude improvement from the current state of the art. So this is the first one. And the second one is about high fidelity fast quantum logic gates. And then for that, we create an entirely different ion trap device. And then that device uses superconducting materials for electrodes. So first of all, we are going to use hyperfine qubit, and then we drive the hyperfine transition, which is normally in the microwave frequency directly, and that eliminates spontaneous emission errors in the gate. But normally this transition is very weak. That means normally we need a lot of power to drive it. But if we use the superconductors as a microwave electrodes, we can reduce the power consumption, and then also we can make the gate a lot faster. So we expect that we can demonstrate a quantum gate 10 times faster with 1,000th of input power compared to the current one. And we also speed up the phonon frequency that contributes to even higher, even faster quantum logic gates. Also, because this is a superconducting technology, we need cryostat to accommodate ion traps. And at the low temperature, we can also lower heating rate. So combining all of this, we believe that we can create a very novel ion trap that can implement high fidelity fast quantum logic gates. And then this is the second one. The third one is about phonons. So ions have phononic degree of freedom. And normally the qubits are represented by the internal states, but phonons are also quantized, and we can utilize this as a qubit as well. And then that is also encoded into quantum error correction codes, and then they are called bosonic encoding. So we are working towards that subject. And then so experimentally, we work on quantum control of multiple collective phonon modes. And then by addressing ions with lasers, we can create beam splitter interaction between those phonon modes. And then importantly, we also have internal states that provides nonlinearity between nonlinearity for the interaction between these modes, and we can create squeeze states. And then combining the beam splitter interaction, we can create cluster states. And then if we superimpose, if we make superposition of those squeeze states, we can create GKP states, and that's the foundation of the bosonic encoding. So this is the third one. So all of these three sub-projects have to be supported by a good, sophisticated fabrication and the characterization technology of ion traps. So that's why we work on this subject as well. So at NICT, the Dr. Kazuhiro Hayasaka is going to work on the fabrication and the characterization of ion traps. And then so we are going to make planar and as well as 3D ion traps by microfabrication. And then so obviously those are provided to the previous three projects. And then also we are going to supply those ion traps to the community to expand the community. And this is also in the internal collaboration between us and then researchers in Germany. I'm sorry, I just didn't introduce the Dr. Kenji Toyoda in this project, as well as Dr. Atsushi Noguchi in the second sub-project. I apologize. But so those people are in our project. And then, so also the Dr. Kenji Toyoda is also going to work on the research and the development for cloud quantum computing using trapped ions. And then, so this is the specification for the ion trap cloud computing prototype. So we are going to build it with ytterbium ions, and we are going to use hyperfine qubits, and then it should have very long coherence times with them insensitive qubit transitions. So we aim at ions a number of ions between 4 to 10 ions. So that's relatively small, but it's in a moderate size. And then we are going to use a micro 3D trap made by NICT. And with this trap, we are going to work on the development of middleware and the software using the prototype. And the aims of this project is so we are going to prepare the technology for the future social or commercial quantum computers. But at the same time, we think that this prototype will be useful in an educational situation. So we can use it as a kind of remote lab of ion trapping laboratory. So yeah, so these are all sub-projects, and this is a timeline. So we are here, and in the 5 years, we want to demonstrate the essential functions necessary for the ion trap module that we envision. And then in 10 years, we want to connect up those modules to make quantum computation possible with those devices. And then in the future, of course, it's a long distance future, but we want to achieve Fault-tolerance with these devices. So let's see. So thank you very much. That's the end.
Dr. Takahashi, thank you very much. I'd like to take one short question from Q&A box. And do you have some comment on, okay, here's the ion and atoms and so on. And here's some proposal using cold neutral atoms or Rydberg atoms for quantum computation. If you have some short comments on these systems compared to trapped ions.
Compared to trapped ions.
Yeah.
Rydberg atoms, so I believe they are pretty nice for quantum simulation. But the thing is, so we cannot trap them very long. So, and then, so that's, I think that makes a big difference. So in ion traps, we can trap ions for hours and then days and so on. So eventually, if we want to make a larger system, so this trapping time problem will be a big issue for them.
Thank you very much, Dr. Takahashi again. I'd like to proceed. Next project manager is Dr. Furusawa Akira from the University of Tokyo. Dr. Furusawa, over to you.
Okay. My name is Akira Furusawa, and from University of Tokyo, and also now I have another affiliation, RIKEN Quantum Computing Center. The title of my talk is Development of Large-Scale Fault-tolerant Universal Optical Quantum Computers, rather long. Let me introduce myself. This is a picture taken at Caltech in 1997. John is here. And my boss was Jeff Kimball. I was a member of this quick project, and I did a teleportation experiment there in 1998. Since then, I have been working on quantum teleportation for more than 20 years. And I'm a windsurfer. My qubit is GKP qubit. Of course, that is invented Daniel Gottesman, Alexei Kitaev, and John Preskill. And that is logical qubit, not physical qubit. So we can make quantum error correction. This is logical 0, and this is logical 1. And we use quadrature amplitude modulation, QAM, which is nowadays used for coherent communication. And actually, that is kind of radio technology, like AM radio and FM radio. As you know, AM means amplitude modulation like this, and FM means frequency modulation like this. And these are orthogonal. And if this frequency, carrier frequency, becomes optical frequency, it becomes quantum complex amplitude, like this. And in that case, AM and FM, X and P, has this type of commutation relationship. That means they have uncertainty relationship. That's why we can make superposition of these guys. That is our GKP qubit. In this case, coherent communication methodology, by using coherent communication methodology, we can make quantum logic like this. For example, by using AM modulation, we can make X operation, I mean bit flip. And also, by using frequency modulation, we can make Z operation. And by using phase rotation, we can make Hadamard. And also, parametric amplification, we can make a squeezing operation. So that is universal Clifford operations. And also, by using non-Clifford ancillary input, we can make universal quantum computer. There are two types of methodology of quantum computing. One is, of course, quantum circuit model. That is quantum circuit. But we take another model called measurement-based model, or one-way quantum computing. In this case, we can use quantum lookup table that is called cluster state. And that quantum lookup table is a superposition of all possible quantum operations or quantum computations. And by using measurement, we can select one of them. Of course, measurement result is random. So to eliminate the randomness, we make operation depending on the measurement result. It is called feed forward. And this process, I mean, cluster state has entanglement. And by using this entanglement and measurement and feed forward is precisely the same as quantum teleportation. So this measurement-based model corresponds to sequential quantum teleportation, which is my favorite. And this methodology is really powerful for flying qubits. That is because if we use flying qubits, I mean photons, in that case, quantum circuit is real circuit. That is totally different situation from the case of ion trap or superconducting qubit. In that case, quantum circuit itself is virtual, just a code or something, score or something. But in the case of flying qubit, we need real circuit. In that case, large-scale quantum computing needs large-scale optical setup. And even worse, if we make some circuit, we can make only one type of calculation. If you want to make another type of calculation, you have to make another setup. So there is no flexibility, I think. But by using our model, measurement-based model, we can solve all of them. For example, we can create ultra large scale lookup table. And actually, it is unlimited because we make measurement before within the coherence time of the fundamental laser. And we already succeeded in 100 million. And also, we succeeded in teleportation like this. And of course, when we change the measurement basis, we can make universal operation. And we can do it forever. And to make it universal, we need multiple qubits input. And for that purpose, we need a 2D cluster state. I mean, 2D quantum lookup table. And for that purpose, we need only 4 squeezers and only 5 beam splitters and only 2 delay lines. And we can create gigantic cluster state, 2D cluster state. And it is published here. And we also succeeded in make calculation, just changing these measurement basis. We succeeded in phase rotation and shear and squeezing like this. And fidelity is really good. And up to here, we are just, I'm talking about just operations. For GKP qubit preparation, we use this deterministic state synthesizer. The mechanism is really simple. First, we create entanglement between inside the memory and outside the memory. That is NN type entanglement. And here we have a generalized measurement device which can be built with coherent beams and beam splitter network and photon number resolving detectors. And we have a shutter here. And by using this generalized measurement device, we project this idler to the desired state. Then we have the state here. And at the very beginning, the shutter is closed, but when we want to use it, we open the shutter. And we are developing our own photon number resolving detectors, which is Professor Takahashi's part. And we already succeeded in this type of device, photon number resolving detectors. And also we already succeeded in memory experiment of qubit like this. At the moment, it is not a GKP qubit, just superposition of 0 and 1. And just after creation, it is like this. And after 100 nanosecond memory, it becomes like this and like that, 200 nanoseconds, 300 nanoseconds, and 400 nanoseconds. It becomes like this. Importantly, we succeeded in memory of phase information. So that means we can all types of state, and we can create, we can build deterministic state synthesizer. And with NTT people, we will do this type of development. At the moment, our quantum computer is based on 860 nanometers, but to build the actual machine or cloud machine, we have to go to 1550. And here is our broadband squeezer for quantum computation. And this is our teleportation chip. And hopefully we can make quantum teleportation, quantum processor chip with this technology. And we already got some results. For example, we succeeded in 2.5 terahertz bandwidth of squeeze light, 6 dB of squeeze light, and all optical detection of that broadband squeezing. This is my final slide. This is our goal. By using 4 OPOs and 5 beam splitters and 2 delay lines and all homodyne measurements, this quantum computer is large scale and universal and fault tolerant because we are using GKP qubit, and even more. At the moment, we are using homodyne measurement. So we make measurement. But in the future, we will replace this one with optical parametric amplifier, as shown before. And in that case, we can build all optical quantum computer with 10 terahertz clock frequency. In this case, we don't have to have Shor's algorithm. Classical algorithm itself is really fast. 30 or 40 years ago, a lot of people believed that optical computer is a next generation computer, but that one disappeared. It was because at that time, optical computer was analog computer. But now it is digital, I mean quantum computer. So my quantum computer means double meaning. One is quantum mechanics, and another meaning is digital for quantum error correction. So I'm aiming at optical computer with error correction. That's why very fast and fault tolerant. Thank you for attention.
Thank you very much, Dr. Furusawa. I would like to pick one question. What is the most difficult part, challenging part in your scheme? Because your plan is sounds very promising and well prepared towards fault tolerance. What is the most difficult part?
I should say everything, but so our photon number resolving detector is has 1-to-1 correspond to atoms. So if our fidelity to GKP qubit becomes very high, we need more photons. And I'm not quite sure how many photons can be measured by using photon number resolving detector. That is the most difficult question. At the moment, up to 10 or 20 would be easy, but I'm not quite sure 100.
Thank you very much again, Dr. Furusawa. I'd like to proceed. The next project manager is Dr. Mizuno Hiroyuki from Hitachi Limited. Dr. Mizuno, over to you.
Okay, my name is Hiroyuki Mizuno from Hitachi Limited. Today, I'd like to introduce our project titled Large-Scale Silicon Quantum Computers. So firstly, let me share the background of quantum computer development, and I'd like to show our directions. This graph shows the number of qubits over decades. Our final goal here, fault-tolerant universal quantum computer requires a huge number of qubits, 10 to the power of 6 and more. NISQ hardware here is expected to be available within the next 10 years, and some useful algorithm has already been developed, as shown here. This is near-term goal, but again, we also need to integrate more than 1,000 qubits. And today here, quantum computers using superconductors are the world leaders in the number of qubits and is approaching to the near-term goal. Silicon quantum computer has been expected to achieve large-scale quantum computer because of their potential for scaling. The potential is true. However, the gap between silicon and the superconductor is increasing in terms of the number of qubits. Obviously, we need to rethink the purpose of using silicon technology to overcome this situation. This slide shows our direction for utilizing silicon technology. Silicon technology has two aspects. So far, we have used silicon technology to reduce the size of qubits, as shown here. Small size of qubit has advantages such as it has strong exchange interaction between qubits. However, the small size make it difficult to control the qubits, and also it induces noises such as crosstalk. And silicon technology has another aspect. It is, I shown this here. It is the ability to integrate many transistors on the single die. It may not be good to compare transistors and qubit on the same level, but for example, the chip in current Apple's iPhone 12 has more than 10 billion transistors. What is surprising is that the chip is not a special one. It is widely distributed in the market. So the power of silicon technology makes it possible to control the qubit precisely with control circuitry integrated on the same chip. And also, many qubits with uniform characteristics can be integrated. We need to take these advantages of the integration to overcome the cons of this small silicon qubit. This is the current setup. Qubits are implemented here. The lowest temperature region in the fridge. All signals for controlling qubits are from the experimental equipment implemented outside the fridge. Therefore, as shown in this photo, the wiring is miserable and it is quite difficult to control the qubits precisely. Many researchers are currently developing control chipset in which several control and measurement circuits for qubits are implemented. It looks much better but the wiring situation between silicon qubit and this control chipset is the same. Our target is here. All the control and measurement circuit are going to install inside the bridge. In particular, key circuits are integrated on the same die of qubit. As I said before, I would like to take full advantage of the power of silicon technology to overcome the cons of small silicon qubit. Of course, circuit integration generates heat problem. It adversely affects the operation of qubit. To solve them, we will develop some technologies such as hot silicon qubit and environmental monitoring. Recently, implementing control circuits in the 4K region of the bridge becomes one of the trends. This is an example of a control chipset called Force-Rich 2. It was developed by Intel and details of the chip were disclosed in 2021. It operates at 4K, 3 to 4K temperature. In addition to this kind of chipset, we are now developing a QCMOS process to integrate key control circuit on the same chip as the silicon qubit array. It operates at 100 millikelvin and can further improve the control capability of each qubit. We are developing 100 millikelvin CMOS operation technology and a hot silicon qubit. This slide shows 2D qubit array integration. In order to implement many qubits, the connection topology of each qubit is very important. When using silicon semiconductor technology, it is effective to arrange qubit in a form of two-dimension array like a memory circuit and connect the qubit vertically and horizontally. Some ideas have been published and studied. This is from the University of New South Wales, and this is from Caltech. And this is from Intel. This is 1D structure, but it is really fabricated and measured by Intel FinFET technology. And now we are developing this one. As shown in the figure, qubits are formed in the self-aligned process between qubit transistors that control the coupling of qubit. This structure minimizes the changes from the standard CMOS process. This slide shows our R&D structure. As I mentioned earlier, to maximize the power of silicon technology, we need to vertically integrate the development from quantum device, process integration, circuit and system, architecture, and software. Although the quantum computer development has shifted from the research phase to development phase, scientific innovation in quantum device physics and algorithms are still essential. So collaboration between industries and academia becomes key. This figure shows an overview of our system. Hitachi is mainly in charge of quantum computer system, including system architecture, silicon qubit array, high precision qubit control, and reader circuitry. Cryogenic multi-chip mounting technology and environmental monitoring technology are from Professor Nagata group from Kobe University. In addition, Tokyo Institute of Technology, Processor Kodera Group will develop a technology called silicon qubit that allows silicon qubit to operate stably in as high temperature environment as possible. Furthermore, Riken, Dr. Nakajima Group will be in charge of quantum operation by small-scale quantum circuit. In addition, we are planning to collaborate with Professor Kowashi project at the University of Tokyo on solution for quantum error, and Professor Yamamoto's project at Osaka University on quantum network between silicon qubit arrays. I believe that this is important to work with the collaboration of as many researchers as possible to develop silicon qubits. So I'm trying to build an open development system aiming at early development of silicon qubit chips by learning from the open source software method. The Moonshot program is here. One of the R&D community, I think, Hitachi is a distributor of the developed quantum chip and the chipset, and will supply these chips to these communities. In the future, when Hitachi provides solution to customers, it will build solutions through this closed development on the right. This slide shows the scenario and milestone for achieving the goal of our project. The final goal is, fault-tolerant universal quantum computers. In order to demonstrate the performance advancement of quantum computer over classical computers, it is necessary to improve both qubit quantity as well as quantum quality, such as fidelity to enable error-tolerant quantum operations. Conventional approach is focused on quality and is increasing the number of qubits one by one. Companies such as IBM, Google have taken this bottom-up approach with approximately 100 qubits. In contrast, our approach utilizes the advantages of silicon to integrate many qubits into 2D array in parallel with bottom-up approach. Subsequently, our unique top-down approach targets the utilization of quality, exploiting digital technologies to control the qubit. In summary, large-scale integration of qubit is the key to achieving fault-tolerant universal quantum computers. Silicon quantum computer has been expected to achieve large-scale one because of their potential for scaling. However, in fact, the scale of silicon qubit has not advanced, so we rethink the purpose of using silicon technology, I think. That is, in addition to using silicon technology to maximize the qubit structure and improve the accuracy of qubit operation, we use silicon to integrate many qubits uniformly, that is 2D qubit array, and to integrate circuit to control the qubit on the same die, that is QCMOS process. Furthermore, to maximize the power of silicon technology, we will develop several technologies such as hot silicon qubit and environmental monitoring. The development of silicon quantum computer requires scientific research on qubit arrays as engineering technology that realizes precise quantum operation. Our project builds a collaborative system between academia and industry for that purpose. We would also like to build an open development system for silicon qubit, aiming at early development of silicon quantum chips by learning from the open source software method. Thank you.
Thank you, Dr. Mizuno. I'd like to take one question from Q&A box, and I believe that the silicon technology is the most advanced in the classical world, the most advanced technology processing informations on the machine. Whereas so many companies and groups are working on silicon quantum computer. However, in contrast to superconducting qubits and ion qubits, it seems very difficult to form a quantum circuit on silicon technology. So what is the cause? Why it is so hard to build a quantum circuit on silicon technology currently?
Okay, thank you for your question. And this is very difficult question, as a very common question for silicon people. And I think there are several reasons. One main reason is, as I said in my presentation, silicon qubit is very small, and to make, for example, silicon qubit, silicon quantum dot, we need to arrange just one electron on each dot. So it is quite difficult to control each qubit precisely. So even if the qubits are arranged in an array structure, it is still difficult to control the qubit. I think it will take some trial and error process. So I think fundamentally the reason is the qubit is very small in silicon qubit computers.
Okay, thank you very much, Dr. Mizuno.
Thank you.
The next project manager is Dr. Kosaka Hideo from Yokohama National University. Dr. Kosaka, over to you. I forgot to mention that the next two projects are quantum communication network projects.
Okay, thank you very much for your introduction. I am Hideo Kosaka from Yokohama National University, Japan. I'm in charge of project manager of quantum network. And the title of the project is Development of Quantum Interfaces for Building Quantum Computer Network. Okay, and then here's the context of this talk. And first I talk about research field, and then that will be followed by technology roadmap, research concept, and required functions. And finally, I talk about target performance. As you heard today, we are going to create a fault-tolerant universal quantum computer, and we have three categories. And my charge is a quantum network to create an interface with memory to connect the hardwares, especially for superconducting qubit in this case. And finally, of course, we're trying to apply to other qubits like trapped ions, silicon quantum dots, photons. And actually, we have also trying to have byproducts like quantum internet or blind quantum computing or quantum sense network. And as you know, that quantum interface is very important to connect all other fields like quantum communication and quantum sensors. Also, we're going to make a blind quantum computing with computers and the quantum sensor network. So we're going to create quantum interface for quantum network. And here I just show you the So here I show you the roadmap created by the Cabinet Office in Japan. And here actually summarized the project from here now on to the 20 years, right? So they have decided 4 categories in this quantum network, and we are going to focus on especially the quantum memory and the quantum interface here. So we have a lot of milestones in this purpose. So we just mentioned that the fault-tolerant logical memory is very important to have this quantum memory to scale up the quantum repeater. And that's actually similar to the quantum interface here in this project. And the quantum interface, actually we have a lot of things to do, but the first thing we have to do is the quantum media conversion between a lot of qubits. First, we have to connect optical photons to quantum memory, and then we're going to connect the superconducting qubit to quantum memory to make a distributed quantum computer in this project. So how to make a quantum computer network? So as I said, so many times the quantum media conversion is very important to have interface between quantum computer to network, and that will make a distributed quantum computer, right? And then in this project, we actually focused on NV center or other color centers in diamond under a zero magnetic field to interface optical photon or microphoton with memory. And then this kind of memory is very important to purify or error correction or fault tolerance. So I show you the detail. So here's the research concept of this project. So as I mentioned, that we're going to make a distributed quantum computer to connect the noisy intermediate scale quantums with optical photons in the network. So that's why we need the interface. The final, actually, in the long run, we are going to connect this quantum computer to the quantum internet that have also the sensor and storage, also a human here, right? To make a binary computation or quantum sensitive communication, okay? And then to make this quantum interface, we are going to make a concatenated quantum media conversion, well, maybe people call this transducer, right? But in this project, we've trying to connect a lot of actually quantums from the superconducting qubit to optical photon in the network by actually microphoton and phonon and spin in between them. And then to make this also concatenated quantum media conversion, we need to have a lot of kinds of cavities to deal with microwave photon or a piezo resonator or photonic crystal, which actually called the optical mechanical cavity. And in the middle, we need to have a quantum memory. In our case, that is the NV center or silicon vector center in diamond that has a spin memory that has quite long memory time, like over a minute. And then to purify the state by heralding and then error correction. So we have a lot of candidates for the quantums, as you heard, ions and silicon qubits or superconducting qubits or photons. But we also have another qubits, diamond qubits, that also show high performance in speed and fidelity and also the memory time. So no less than other qubits. So we're going to use this diamond qubits as an interface, okay? So now here's more detail of the diamond. We have a lot of actually spins in diamond. The variety is very important in our case. So we have vacancy here that holds several electrons, and that can be used for quantum process quite fast, quite as fast as gigahertz. And also we have some buffer spin on nitrogen nuclear spin. And the important thing here is the quantum memory on the carbon nuclear spin of isotope carbon-13, that we're going to use this kind of memory to purify the state. And I want to mention that a diamond can be also ultra compact quantum computer and sensor, but now just use quantum this as a quantum interface here. Sorry. So this view graph shows that our current status and the required functions to make a quantum interface. So we need to do a manipulation, memory, and readout, and those combinations in diamond qubits, right? And the important thing is the magnetic field, because we're going to connect with the superconducting qubit. We cannot apply a strong magnetic field. So the zero magnetic field is very important, and these numbers actually under this condition. So here, the top 4 shows this single manipulation, like quantum manipulation fidelity, manipulation time, or memory time, or readout fidelity is around here required. And currently we have demonstrated this kind of numbers that has to be boosted up here. And below we have a combination protocol like electron photon entanglement generation and photon to spin quantum state transfer and error correction or coding or Bell state measurement. Also be over 99% or more, I guess. So currently we have a lot, about 90%. So we have to have a more improvement. And also we want to have a memory, a lot of memory, individually accessible. So it has to be more than 100 or maybe 1,000. Currently we have 10 memories. This shows our recent demonstration of the quantum teleportation transfer based on the quantum teleportation scheme. So we have transferred and stored the quantum state from optical photon to a quantum memory on diamond carbon right here. So based on the quantum teleportation. And the mechanism is very simple. Just prepare the entanglement between the persistent electron with the carbon memory, and then put the photon to be absorbed by the electron. And in that instance, the photon information is transferred indirectly to the quantum memory here by the teleportation scheme. So in this project, we're going to make this optical photon into a microphoton created by superconducting qubit, and then want to transfer and store the quantum state to a quantum memory here. And then we can combine the superconducting qubit to a network photon through the microphoton and the phonon and spin here. And actually, so far, we have actually struggled with creating a nanostructure of diamond. And about 5 years ago, we have always using diamond bulk structure shown here. The size was about millimeter size. And then we made this one scale down, 100 micron, and then more 10 micron and 1 micron. And currently, we're working on this size scale, 1 micron. And we have a thread marginal length structure, and in the middle we have diamond and center here. And then in this project, actually the main purpose to create a diamond photonic crystal or phononic crystal like shown here. And then we are going to dramatically improve the efficiency of the quantum interface or transduction. And finally, we also need a large-scale quantum random access memory consists of NV centers or other color centers. We call this quantum RAM. That should be a 5th generation. And in this actually quantum interface research, we have other activities in the world, especially in the United States. So I just summarized some of the activities here. So speaking about diamond, actually, people have tried to connect with the photon with the Fabry parallel resonator or photonic crystal, or optomechanical crystal, as I mentioned, photonic crystal can be integrated with diamond. See? And also people are trying to put the diamond microchip on the photonic integrated circuit here. And also in the side of superconducting qubit, people are trying to work with phonons actually to connect into photon actually. So actually in this project, we're going to combine all of them from the superconducting qubit, phonon, and spin with using our technology to make a hybrid quantum interface. And then I briefly mentioned about our target performance. The performance actually is defined by the throughput of the transaction. And the throughput is actually has three items: conversion efficiency, bandwidth, and fidelity. And if speaking about efficiency only, we have two things to do. The one thing is the photon to memory transaction. Currently, actually, we are working on around this scale, like 10 to the -4 efficiency with this bandwidth. But by using photonic crystal, we can boost up both the bandwidth and the efficiency to about here, right? And people actually try to make this photonic crystal to around here, but the problem is that they always use strong magnetic field. As I mentioned, if we want to have an integration with superconducting qubit, we need to do this around at the zero magnetic field. That's why we have to work on using NV center here. And then, on the other side, from superconducting qubit to the photon, actually people tried to make this, but unfortunately, by using magnum, the efficiency was around 10 to the -10. And we have to make it 10 orders of magnitude better. And the people actually try to do this by using photonic crystal, as shown here. But as I said, they don't have any memory here. And the memory is very important because they can never be 100% efficiency. That's why we need the purification or error correction. And then we need some kind of quantum system like memory here. In this case, NV center or second efficacy spin. So we're going to make this kind of device to connect from the superconducting qubit to the optical photon and through a microphoton, phonon, and spin. And then we're going to make all kinds of resonators, all connected, starting from the microwave resonator, piezo resonator, and the phononic crystal, and spin and photonic crystal. So the important thing is this memory to purify and error correction, and all the efficiency and speed, of course. And to do this project, actually so many people gathered here in this project. So I would say 33 Japanese best nanotechnology researchers gathered in this project. And we have three categories, and one is the diamond memory team. The team have basically 4 members and other collaborators here. And so many people, actually people working closely together. And like Dr. Teraji in NIMS creates a very pure diamond crystal. And then Dr. Onoda from QST make a color center in that diamond. And Dr. Kato and McKenna and ICE make a nanostructure on that. And then we measure. And then the team of optical mechanical crystal, Professor Iwamoto worked on photonic crystal, and Professor Nomura from Tokyo University worked on the phononic crystal cavity. And Professor Baba from Yokohama National University integrate that cavity with the photonic circuit. And in the final team, piezo microwave resonator, actually so many people actually work together from RIKEN, INICT, Kyoto University, and IST YNU to make the piezo microwave resonator and integrated circuit. And we also work together with Yasu Nakamura, Eroto, and Tsuyoshi Yamamoto Moonshot project. And to summarize, we're going to use the diamond color centers, and that shows high performance in speed and fidelity and memory, and no less than other qubits. And then we're going to combine that kind of diamond with the superconducting qubit and integrate with photonic integrated circuit that enables hybrid quantum interfaces, as shown here. Then we're going to concatenate all the quantum media converter or transducer from superconducting qubit to the optical photon with the microwave resonator, piezo resonator, and photonic optical mechanical cavity with the spins in and the diamond to verify by heralding and error correction. And then a lot of Japanese-based nanotechnology researchers and also maybe other overseas nanotechnology research will gather here in this project. Thank you very much.
Thank you very much, Dr. Kosaka. I'd like to take one question. Your concatenated quantum media converter consists of 5 parts, I guess. I remember, yes. And what is the most difficult part or the bottleneck of these 5 sections?
Okay, thank you very much. That's a very good question. Actually, so many things are very hard. Actually, we're working on NV Center. That part should be easy for me, actually. But others like Photonically are actually very immature in Japan. Actually, we are going to make first a diamond nanostructure. That's pretty hard. And also, this kind of Pierce resonate is most hard part for us because not so many people actually working here in Japan, and trying to combine all the technology with the microwave and the phononic crystal. So all the collaboration is very hard, especially on the creating a nanostructure here. So that's all difficult.
Yes, thank you very much, Dr. Kosaka again.
Thank you very much.
The next project manager is Dr. Yamamoto Takashi from Osaka University. Dr. Yamamoto, over to you.
Thank you very much for the introduction, and for audience, thank you very much for joining this symposium. I'm Takashi Yamamoto, a professor in Osaka University and also Center for Quantum Information and Quantum Biology, and also a graduate school of engineering science. Our project is entitled A Quantum Cyberspace with Networked Quantum Computer. Today, I introduce our project, including our vision, our team, and our next 5-year or 10-year targets for this project. Okay. A part of our vision has been described in the webpage of Moonshot for Goal 6. Our target is to build a large-scale quantum computer by connecting relatively small-scale quantum computers to a quantum network. As you see in the previous talks, many physical systems for quantum computer is explored. So in our project, we will try to provide interfaces of quantum networks for all of those quantum computers as much as possible. And in early stage, it may connect a few quantum computers located closely. Then the size of the network will be bigger gradually, which enables distributed quantum algorithms and quantum internet protocols and so on. So we aim at that finally our project will end up with a quantum version of the current cyberspace. To achieve this target, we will develop various elemental technologies with several expert groups. Here is the overview of our research team. And we have 4 groups dealing with 4 different kinds of physical systems: atoms, photons, and semiconductor, and superconductor. Each of which is run by an expert in each field. And single photon detector technology is a key for creating photonic quantum networks. So we have 2 groups for this topic. And not only our team members, but we will also collaborate with other teams and projects tightly to achieve the goal of this Moonshot program. And I will introduce each groups one by one in the next slides. Our group in Osaka University will focus on developing the networking technology for atom-based quantum computer. The elemental technologies are also useful for other systems, I guess. And our group has a long-term experience on photonic quantum information processing. For example, we have demonstrated all photonic quantum repeater based on linear optics, and also entanglement distillation, and so on. We have actively studied on also quantum frequency converter to telecom photons for a long-distance quantum communication, and also quantum operations on frequency multiplexed photonic qubits. Recently, we also perform atom-photon-based quantum system in collaboration with various groups. Based on called rubidium atomic ensemble, we have demonstrated atom-photon entanglement, and also with the quantum frequency converters, wavelengths of photons are converted to the telecom band. We did a similar experiment with trapped ion in collaboration with Sussex University and NICT. Based on those technologies, in this project, we will try to connect atom array-based quantum computer with photonic network. Atomic array quantum computer is rapidly evolving quantum computer. Each trapped atoms in optical tweezer array works as a qubit, and the nearest neighbor interaction is realized by the Rydell interaction. The size of the array will reach more than 100 sites, and replacing our atomic ensemble by this atomic array quantum computer, we can create multiple atom-photon entanglement, and we can connect the atomic array quantum computers. This is our 5-year target, and to achieve this goal, we need very high performance and multiple single photon detectors. So we have two groups for building high performance and multi-channel superconducting nanowire single photon detectors, SNSPD, in short. Dr. Mickey's group in National Institute of Information and Communication Technology, NICT, will focus on developing high-performance SNSPDs. His group has a long history on developing SNSPD in Japan. Since 2006, they began building SNSPD and contribute to improve the system detection efficiency up to more than 80%. And their SNSPD systems have been installed in Tokyo QKD network and operated almost 10 years in the field. Recently, they have also built SNSPD array with superconducting digital readout for the multi-pixel applications. In this project, his group will further improve the performance of SNSPDs. For single-channel SNSPD, in next 5 years, the wavelength range will be extended to UV regime for trapped ion qubits. The detection efficiency will be more than 95%. The dark count rate will be improved from 10 count per second to below 0.1 counts per second. They also try to establish a scalable multi-channel SNSPD system by combining SNSPD array device technology and optical fiber array. They further challenge monolithic integration of SNSPD with trapped ion qubit devices in collaboration with Takahashi project manager project. The other group of SNSPD is run by Hideki Shimoi and Tsuyoshi Kodama in Hamamatsu Photonics Electron Tube Division. The group is very famous for the products of photomultiplier tube, PMT. They produce many kinds of PMT for various applications. As you know, this biggest PMT here is used for detecting neutrinos in Kamiokande, super Kamiokande, and hyper Kamiokande as well. They established core technologies, for example, high vacuum packaging, thin film deposition, and single photon detection, and so on. Their world's smallest and lightest micro PMT shows their very high level technologies, especially for the commercialization. In this project, in collaboration with NICT group, they will develop multi-channel SNSPD system, including cluster and multiple fiber ports, which will be very close to the commercial product. They will establish manufacturing technology of superconducting thin film and realize stable production of SNSPD with the high performance photon detection technology from NICT. They will also build high performance cryostat, which achieve mounting large number of SNSPD and stable operation for a long time. The 5-year target of this project is the development of 100-channel scale multi-channel SNSPD system and to contribute to the other project, including our team and also the other teams project. Aoki group in Waseda University will develop photon networking technology based on cavity QED. His group has a long-term experience on cavity QED experiment. His remarkable cavity QED system is based on nanofiber with fiber Bragg grating based reflector, and the system is all fiber configuration that leads to the high scalability and high cooperativity. Using this system, his group demonstrated strong coupling with a single trapped atom. Furthermore, they prepared 2 systems and demonstrated the coupled cavity QED system by using those 2 systems. Those are very unique systems in this field. In this project, his group uses this system to generate multi-photon quantum network. Cavity QED system is an ideal physical system to generate various photonic states. They will first try to generate pure single photon qubit state sequentially, which realizes photonic qubit array. By changing the interaction between atom and photon, they will try to generate one-dimensional cluster state in the optical fiber. This is the 5-year target of this project. The remarkable thing is that their system is all fiber system, including Bragg reflectors, and it will be suitable for mass products with the same property. So we expect that once they created one-dimensional cluster state, by multiplying these processes, they will create NISQ scale 2-dimensional cluster state. So this is the 10-year target of this project. Professor Oiwa group in the Institute of Scientific and Industrial Research, Osaka University, will develop various type of networking technology between semiconductor qubits. His group has a long-term experience on semiconductor qubit of electron spin in quantum dot, and they achieved quantum state transfer from a single photon polarization state to single electron spins in quantum dot for quantum network. Also, they have demonstrated the creation of photon-electron pair from entangled photon pair. In this project, his group tries to develop networking technology, especially for silicon qubits. The most promising candidate of semiconductor-based quantum computers. The first method is based on photon spin conversion, which is based on their previous researches. They first convert the state of the photon into the spin state in a semiconductor quantum dot. Then the spin state will be transferred to silicon qubit to NISQ device. Based on this method, they can achieve the networking among distantly located silicon-based NISQ devices. The second method is to connect closely located NISQ devices without optical photons. Now, there are several methods. Now they start discussing several methods to achieve this target in collaboration with Mizuno team in Hitachi. And 5-year target of this project is to develop photon silicon qubit interface and silicon qubit coupling for creating large scale NISQ devices of semiconductor. Kubo Group in Okinawa Institute of Science and Technology, Graduate University, OIST, will develop networking technology between superconducting qubits. He's a young and active researcher in the field of hybrid quantum systems with superconducting qubit and spin ensemble in solids. He has demonstrated coupling between electron spins of NV centers in diamond and microwave in superconducting circuit in 2010. Then he continuously studied such systems and demonstrated quantum limited electron spin resonance and observed Purcell effect on spins in solids. Now he is his own group in OIST as a group leader. And in this project, based on his activities, his group develops quantum transducer with spins in diamond, which translates microwave photons from superconducting qubit to optical photons. The mechanism of the transducer is similar to the quantum frequency conversion in optical regime. And in principle, the conversion efficiency from microwave to the optical photon is 100%, and the coherence is preserved in the conversion process. Therefore, quantum state of the microwave qubit will be translated to optical regime without destroying the quantum state. Optical flying photon can be used for carrying the quantum state in a dilution refrigerator to the optical fiber at room temperature and making a quantum link between superconducting quantum computers located in different dilution refrigerators. So towards this quantum link between quantum computers, KUBO group tried to demonstrate the conversion of non-classical microwave photons from superconducting qubit in next 5 years in collaboration with Yamamoto, Tsuyoshi Yamamoto team in NEC and Nakamura group of QLIP project in Beacon. They will kindly provide superconducting qubit devices to KUBO group for the demonstration of non-classical state conversion. This is the summary of our project. As I mentioned before, our team will develop elemental technologies of quantum network for diverse quantum computers. Our 5-year target is to demonstrate the full lineup of elemental technologies for networking quantum computers. Based on those technologies, we will try to demonstrate large-scale quantum computers with quantum networking in 10 years. Those targets will be achieved in collaboration with other teams and projects. Thank you very much for your attention.
Thank you very much, Dr. Yamamoto.
Thank you very much.
I would like to take one question from the Q&A box. This is a little bit, okay, the Moonshot, the first 5 years actually does not accommodate quantum internet research due to the limited budget. But here's a question from the floor. Do you have target? Do you have the operation speed target for quantum networking repeater?
Oh, operation speed.
Speed, yes.
Wow. Yeah.
If you have a short question, short answer.
Yeah, speed, because the speed, necessary speed is depend on the application. So I'm not fixed the speed of the speed because multiplexing also helps the speed up. So I think the important thing is the next 5 or 10 years is for me is the multiplexing.
Thank you very much.
Then we can speed up the network.
Thank you very much. That question is from Goto Hideki from NTT Research Laboratory.
Thank you very much.
And another very short question. Your project is several things in parallel, so there will be no bottleneck maybe, but what is the most difficult part of your project?
Yeah, but in the short term, I think we can step up and improve the technology. But at the end of the let's say to make a larger larger quantum computer, we need to increase the efficiency of the transducers and detectors. So at that point, we need to, how to say, it's become harder and harder, right? So that part is very hard, I guess. We need to continue to improve the technology.
Thank you very much, Dr. Yamamoto again.
Thank you very much.
The next project manager is Dr. Kowashi Masato from the University of Tokyo. And he is the last speaker of this session. Dr. Kowashi, over to you.
Thank you. Okay. Hello, everyone. I'm Masato Kowashi from University of Tokyo. And I would like to introduce my project titled Research and Development of Theory and Software for Fault-tolerant Quantum Computers. So we have already heard about the 6 projects of experimental studies. 4 of them pursue constructing quantum computers based on different physical systems, superconductors, trapped ions, optics, and silicon, and with 2 projects for networks. Now, the Theory and Software project is a kind of cross-divisional project, gathering theoretical researchers into a single project. So I think when you design the structure of the whole program, there would also be a possibility of deploying theoreticians in each of the project. But Director Kitagawa-san's decision was to place great emphasis on tight collaboration among theoreticians. And now let me review the structure of a fault-tolerant universal quantum computer. So we can regard it as being made up of many layers, like hardware at the lower layers and software at the upper layers. And in the bottom layer, physical qubit, which is a basic hardware unit to store quantum information, is constructed using various physical systems like superconductors, semiconductors, ions, and optical pulses, and so on. And for the moment, we don't know which of the physical system is the best. And that is also the reason why the Moonshot program has 4 different projects dealing with different physical systems. Now, at this layer, the focus is mainly put on the static or stationary properties such as lifetime, spectral shape to characterize its Hamiltonian, and the mechanisms for causing interaction between qubits. And also the scalability is, of course, a very important requirement for the physical qubits. Now, the next layer deals with the basic control of these physical qubits. Like initialization, gate operation on single or 2 qubits, and the readouts. So control is a dynamical thing, typically realized by applying control pulse to change the energy structure and interaction. So theoretically, it is treated as a time-dependent Hamiltonian. So compared to the bottom layer, things are more complicated with many parameters to fiddle with. And it is often not an easy task just to learn what is going on in the qubit system created in the laboratory, let alone finding out how to make a good calculation of these parameters. So it is very important to develop clever method of characterizing or diagnosing the dynamical response of the system, and also a good simulating software to solve the time-dependent Hamiltonian. Next layer is the defining one for the fault-tolerant universal quantum computer. So here you align many physical qubits and prepare them in a state of quantum entanglement. Now this bunch of qubits are called logical qubit, which stores single qubit information spread over many physical qubits. Now, thanks to this redundancy, even if some of the physical qubits are corrupted and suffer from physical errors, the encoded logical single qubit information survives in the sense that it is possible to repair the damage. And of course, these qubits keep corrupting even while we do the repairing. So it is a kind of chasing each other around. And we have to continually do this error correction operation. Now, this process of error correction is composed of extracting the information about the physical errors, which is called error syndrome, and the decoder determining the location and the nature of physical errors, and doing the correction operation to the corrupted qubits. Measurement of the syndrome is the combination of these gate operations and readouts, which are typically massive parallel operations. Now, this syndrome itself, unfortunately, does not tell you directly the location of errors, but a kind of very indirect hint about them. So you need a good classical processor to figure out the location from the hint. So sometimes the qubit and processor require entirely different temperature to function properly, so that they must be separated. Then the boundaries of this line here also become the things to worry about. Now, having logical qubits here, the next thing we need is the control of the information stored in the logical qubits, which are the logical version of these primitives, initialization, readouts, gate operations. So the complication arising here is that among various operations that can be easily implemented at this physical qubit level, only a short list of the operation can be realized for the logical qubits. Since we are talking about universal quantum computer, the list must include enough operations such that we can compose any quantum circuit from the list. So this is an example of such a list, and we can prove that any quantum program can be composed from these operations. Now, this kind of assurance is of course good, but practically we need much more than such an abstract mathematical proof of universality. What I mean is that to say, in the top layer, you are given a task to carry out in the quantum computer, but what is provided from this layer is this small instruction set. So we need a layer to find a good way of decomposing the task into instructions given in a set. Now, it turns out that these instructions are by no means homogeneous and tends to have very different properties. So some of the instructions can be carried out simply and quickly in parallel with the error correction loop here, but others are much more complicated and must be pipelined with error correction, leading to a big latency. So the compiler should just take into account such various properties in finding an optimized decomposition. Now, let me define the main mission of the theory software project. So the goal of this Moonshot program as a whole is realization of fault-tolerant universal quantum computer that will revolutionize economy, industry, and security by 2050. Now, until that time, the performance of the actual devices will steadily increase thanks to the effort of experimental researchers. On the other hand, as we have seen, the fault-tolerant quantum computer is a very, very complicated system made up of multiple layers. And there are so many possibilities of designs and choices of various parameters. So that means that theoretical researchers can contribute by exploring these possibilities to lower the bar here. That is, to relax the requirement for the device performance. So the responsibility of the theoretician is to reduce substantially the level of requirement for the device performance. So our goal is to make this curve and this curve meet by 2050, like this. Now, what can we do toward this goal? So the participants in this project are very strong theoreticians across Japan, and I'm truly happy that they agreed on joining this project. And so in each of these layers, I expect many good results. And at the end of the program, which is 10 years from now, this bar will surely be lowered. But as I said earlier, we have a very unique opportunity of gathering a wide range of researchers like this. So I would like something more, that is something that helps to accelerate this trend of this curve. So, and that something is the cross-layer co-design model. Now, a fault-tolerant universal computer is a complicated system with many layers, as we have seen. Now, a cross-layer co-design model encompasses metrics and trade-off relations in each of these layers, and through optimizations and simulations, predict the performance of the entire system of fault-tolerant quantum computer. So maybe let me give you an example, which I hope will make it clear what is the issue here. So this is a recent work made by a collaboration, including participants of this project. This is a proposal about designing a decoding module which works in a low temperature, aiming at avoiding the bandwidth problem in syndrome transmission. Now, in this paper, the code distance and the physical qubit rate, error rate are specified, and then logical error rate is optimized over the various design parameters and external constraints. And they also computed required clock cycles, which is essentially the time taken to decode. Now, this is what they can do within a single layer. But in the big picture, if you want a big picture, then these two numbers actually affect the latency and the error rate of the instruction used by a compiler. So the optimization would be affected by what's going on in the upper layers. In addition, this number here restricts the interval of syndrome measurement. So through the parameters appear in the lower physical layers, eventually this affects the physical error rate P here. So P is no longer a parameter to be specified, but rather one of the variables in the optimization. So to really understand what is going on, it will be very helpful if we have a model to cover all the layers. Now, I believe that the construction of such a model will benefit the project in a variety of ways. In the development stage of the cross-layer co-design model, I hope it works as a hub to promote research in the theory software project. Through the cooperation to build such a model, interactions are encouraged, and the participants from different layers will be able to communicate in the same language. It also helps them see the big picture toward the goal of the Moonshot program. And once the prototype of the model is constructed, it will work as a pilot to guide the researchers in the Moonshot program toward its goal. So the researchers tend to encounter trade-offs in various levels, like the choice of parameters in hardware design, or in a higher level, the issue might be maybe how to spend limited time and money. So since it is hard to know what is the best if you are confined in a single layer, so co-design model here will give you a navigation in the big picture. Now, as the model extends its scope, it may serve as an advisor in determining the direction of the program, because optimization over multiple layers may reveal a true bottleneck, and the comparison of different approaches through the model may clarify pros and cons. Finally, the model can eventually put together the state-of-the-art results in each layer to produce an optimized design of fault-tolerant quantum computer. So it serves as a kind of a dynamical blueprint. So I thus believe that the construction of co-design model will contribute to make an accelerated trend here. Now, I would like to point out another unique feature of this Moonshot program, which is the inclusion of researchers proficient in quantum networks. Naturally, this is the best opportunity to explore the possibility of distributed architecture in building quantum computers. For some of the physical systems with matured integration technology, it will be possible to put everything on a single chip, and it may not be necessary to adopt distributed architecture. On the other hand, for other systems, there is a limitation on the number of physical qubits in a single node. So we have to connect multiple nodes by quantum channels. So, of course, there are some drawbacks in this structure. It requires good interconnectors like microwave connectors and transducers between microwave and optical ranges, but experimental groups are making good progress in that. And the fact that information must travel a certain distance here will lead to additional decoherence and latency, and sometimes the connectivity between qubits will be lower. And compiling may become more complicated if it has to take into account this kind of non-uniform structure. On the other hand, there are also good things about this distributed structure. So the issues arising from integrating too many qubits are mitigated, and we may connect nodes made up of different physical systems in such a way that we may somehow benefit from advantage of each of the different physical systems. And there is a freedom in connecting which qubit to which qubit, implying that we may no longer be restricted to 2D structure, maybe 3D or maybe 4D. And the non-local encoding over multiple nodes will make it more robust against burst errors and against fault in controlling hardware. So there are many interesting possibilities, and we don't know much about it yet. So it is exciting to explore in this direction. Finally, I would like to introduce participants in this project. So the construction of cross-layer co-design model is led by Dr. Yuki Tokunaga. And people dealing with hardware-specific theories are Professor Yasuhiro Tokura for semiconductors, and Professor Kazuki Koshino for superconductors, and optics by myself, and Dr. Franco Noli for software QTIP to solve time-dependent Hamiltonian. And quantum error correction methods are led by Professor Keisuke Fujii and Professor Kai Enomoto. And distributed architecture is assigned to Dr. Koji Azuma and Professor Lodny Van Meter. In addition, these up-and-coming young researchers pursue breakthroughs in their own unique ways. So I apologize, I have only shown here the group leaders assigned to each institute. And each group in the university has energetic young researchers and students. And groups in other institutes have not only young researchers, but also renowned senior researchers. So I'm very glad to be able to work with these excellent researchers and to collaborate with a wide range of experimental projects to tread an unexplored path leading to the moon. Thank you very much for your attention.
Thank you very much, Dr. Kowashi. I would like to ask one question, but the common question and maybe a difficult to answer. What is the most challenging part, most difficult part of your project?
Well, maybe difficult part is, okay, as a science, actually, the fact that we don't know yet whether, for example, this distributed structure is eventually good or not. So we don't know yet. Yeah. So, but still, we feel that there is a big interest in possibilities. So we are pursuing something. We are not sure, but maybe it's almost all the case in scientific things. And also another thing as a project manager, I think it's a difficulty. It's a balance between doing systematically doing something, and also hope to have a breakthroughs. Sometimes it's a conflict to each other. So maybe it's a balancing between them. It's say something I have to keep in mind.
Thank you very much, Dr. Kowashi. We forgot to mention that Moonshot Goal 6 involves these 7 very ambitious project managers, but also about 50 PIs and 200 researchers from about 30 institutions, including industries and universities and research institute. Now we have heard from all the project managers. I hope their presentation helped clarify what we are doing here at Moonshot Goal 6 and how we intend to achieve our vision of a fault-tolerant universal quantum computer. Thank you very much for listening, and thank you very much for all the speakers.
Thank you, Dr. Kitagawa. That concludes the project's overview session. Finally, I would like to invite Dr. Hamaguchi Michinari, President of JST, to give his closing remarks by video.
Minasan, konnichiwa. JST 理事長の浜口です。本日は JST のシンポジウムにご参加いただきまして誠にありがとうございます。ムーンショット型研究開発制度はご存知の通り、野心的なムーンショット目標の下で研究開発を進める制度です。現在、国によって7つの目標が設定されておりますが、そのうち4つの目標を JST が担当しております。昨年2月、新型コロナウイルスの問題が深刻になり始めた頃に、提案募集を開始し、プログラムディレクター、PD とアドバイザーの皆様のご尽力により選考を進め、夏の暑い盛りお盆の時期に連日のようにインタビューをしていただき、昨年9月にプロジェクトマネージャー PM の採択を決定いたしました。その後、目標達成に向けてより効果的な研究体制にするために、数ヶ月にわたる PD と PM の皆様のプロジェクトの作り込み作業を行っていただき、いよいよ研究開発が開始されることになりました。残念ながらコロナのためウェブ形式の開催となりましたが、このように皆様とムーンショットのプロジェクトが始まったことをご紹介できるまでに至ったこと、大変喜ばしく思います。また、今日まで本当に大変な作業をしていただいた、プログラムディレクター、アドバイザー、そして PM の皆様に改めて深く感謝申し上げます。それと同時に 国として非常に重要なプログラムを運営していることに改めて大きな責任を感じております。さて、このムーンショットという言葉ですが、その語源はアメリカのジョン・ F ・ケネディ大統領が月に人間を送り帰還させるという計画を立てたところから始まっております。当時私も若い学生でありましたが、まさかと思うような計画でありました。そんなことが本当にできるのだろうか。そこから始まったプログラムは現実には60年代は不可能でありましたが、70年に至り月に人を送り、そうして帰還させ、現実にケネディが考えたことができることを証明しました。さらにこのムーンショット計画の中でさまざまな科学技術が開発され、多くの企業が発展していきました。今回日本でもムーンショットプログラムを開始するわけですが、ご存知のようにここで掲げられたテーマは大変困難なものであります。この困難を成功に導くためには、私は3つの要素が必要であると思います。それは何か。第一に、このプログラムに参加していただいた皆様方の強い熱い情熱であります。一見不可能に思えることを挑戦するには情熱なしにはできません。さらにその困難の向こうに大臣の申し上げておられたウェルビーイングがあることを心に深く留め、情熱を維持していただきたい。第二に、これから直面するであろうさまざまな困難、山や谷を越えていくためには強い意志が必要であります。熱い情熱と強い意志、これを持続的に維持していくために第三に必要なことは連携であります。同じムーンショットの目標を掲げた皆さん方が今日のように一堂に集まれ、シンポジウムを開き意見交換していく中で連携が生まれます。その中で連携をすることによって困難を超えていく情熱と強い意志を持っていただけることを期待しております。これから皆様が目標とされるムーンショット計画は大変壮大なしかし厳しいプロジェクトであります。ぜひ強い情熱と意志を持ってゴールに到達されることを心から願います。私ども JST も組織を挙げて皆さんを支援し、このムーンショット計画が成功に導かれることを期待しております。本日はご参加いただきましてどうもありがとうございます。来るべき2050年の社会を見据えて、今日から一歩一歩作業を共に進めていきたいと思います。どうぞよろしくお願いいたします。
Thank you, Dr. Hamaguchi. That concludes our program for today. When you leave Zoom, you will be redirected to our questionnaire. We look forward to receiving your comments. Once again, thank you everyone for joining us today, and we very much hope to see you at the next Moonshot event. Goodbye.